Hello, everyone. Welcome to day 3 of CogX. Good morning. I hope that everyone had a lovely evening last night, whether you were watching the first 2 days of CogX or whether this is your first day. A warm welcome to the final run of programming here on the cutting edge stage. My name is Gemma Milne. I'm a science and technology writer, author, and podcaster, and I'm going to be your MC for today, taking you through the many wonderful sessions. This is a packed day on this stage and many wonderful sessions that we have coming up. Speaking of which, we've got our first session this morning kicking us off. It's called A Glimpse into the Future with Science Partners from Aaron. And I'm going to introduce you to the moderator of the session who's going to take it away. Please join me in welcoming founding and managing partner of Aaron Innovation Capital, Alice Newcomb Ellis. Thank you very much.
Good morning. So I'm Alice, and founding partner of Aaron, and I'm privileged to call my partners a special group of Cambridge University's finest minds and most successful commercial scientists, including Sir Shankar and Professor Steve Jackson. You'll hear more from them a little later. Could we have the first slide, please? Two years ago, I visited the NASA Space Center in Houston. It's an immense structure, and in this stunning gallery, you can gaze up at the stars in wonder and awe of what human endeavor can achieve. People often ask me what was the catalyst for setting up Aaron. For me, that was it. I often think back to that moment with particular pertinence at this difficult time. What can our collective human endeavor and ingenuity achieve? What does the future look like, and how can we each contribute? The answer will be different for every one of us, but for us at Aaron, we set up in order to help create that future, to nurture and mold advances that will have a positive impact for all of us. At Aaron, we believe we're at the cusp of a period of possibly the greatest acceleration in progress and change that the human race has ever seen, powered by technology. Today, we're going to give you a glimpse of what we believe that future will look like. But first, for those of you not familiar with Aaron, I wanted to say a few words about us. Aaron focuses on 4 domains with one overarching theme: to invest at the intersection of deep tech and deep science in opportunities that are transformational and highly commercial. That intersection is an operative word. We believe wholeheartedly that the future will be cross-domain. We define our own mission and follow our own agenda. We understand the things we invest in and insist on an edge in order to have a right to invest. Our edge can be complexity, understanding in spaces others can't access, seeing what others don't, or contribution, being able to add genuine value. We believe we have 5 key differentiators. First, my science partners are intrinsic to our model. Their prior technologies are today worth over 100 billion combined. We pair this with sharp and dynamic investment talent to give us an edge to source, diligence, and scale deep tech, deep science companies. I've been overwhelmed by their commitment to Aaron's success in sourcing, in nucleation of opportunities from scratch, in the all-important deep diligence of deep tech companies, and in mentoring and support they provide to our founding entrepreneurs. Entrepreneurs come to us as a group they trust and respect, and a group that can have a differentiated impact on their success. Second, we accept risk, considered highly rewarded risk. We do not chase lower-end, lower perceived risk opportunities that we believe by definition erode returns. We invest in groundbreaking companies that will penetrate or create massive markets. Third, we don't just invest, we build, applying Clay Christensen's theories of disruptive innovation. We actively support nascent companies, or even nucleate companies from scratch, to turn a big idea into an even bigger commercial reality. Fourth, we have value corporate and strategic, as well as pure financial LPs. They're very important to us. We have deep relationships where we help ensure our LPs are the disruptors, not the disrupted in the changes that lie ahead. And they provide invaluable support for our portfolio company teams, with pilots, access to networks, insights, and in some cases, potentially access to billions of customers worldwide. Fifth, we treat our entrepreneurs well, motivating and incentivizing them to succeed. We're very proud of the teams we've invested in to date. Each of our companies solves a critical problem, a limiting factor to transformational progress with a solution that has the potential to disrupt a market. And as Aaron, our values are something we take very seriously. In sum, we feel we have a differentiated model to support exceptional entrepreneurs. And now I would like to hand over to Steve to give his perspective.
Great, thanks Alice. It's been a huge pleasure and a great privilege to be part of the Aaron science team over the past 2 years. Working with Aaron is allowing me to use my insights and knowledge in the realms of human biology, genetics, and platform technologies to identify exciting new scientific and technological opportunities that have the potential to change the world for the good. Moreover, it's been fantastic working together with a group of accomplished and highly passionate individuals who are excited about not just their own domains of science, but the intersections between these and others. Because as we're all aware, in many instances, the most transformative and impactful developments in science arise at such interfaces. And in this regard, I found it tremendously enlightening to learn about so many areas outside of my own primary areas of expertise, and to connect up with the passionate scientists involved in Aaron and the entrepreneurs that we're interacting with, who are coming to us or whom we're finding. And then, of course, working with them to help build their exciting new businesses. Now, one of the key things about Aaron is that we don't just sit back and wait for things to happen. We're out there continually, actively looking for new opportunities, and in many cases, identifying opportunities before they come to us. And of course, then when we identify or are approached by scientists and entrepreneurs with aligned ideas and discoveries, we actively work together with them, in some cases very early on, to evolve and nurture these ideas. And in these kinds of ways, we're helping to craft the big visions, the types of opportunities that you'll be hearing about from us today. A little bit later on, I'll provide a recent example how we identified one exciting new opportunity, and that led us to nurture the development of a new company, which is now moving forth with its vision.
Thanks, Steve. So now, on to the future. As a group, we're constantly thinking ahead, never resting complacent or sitting still. We want to understand before others believe. These are the few of the domains that we're very excited about, particularly at this time of change. And if you have developments in these spaces, please feel free to reach out. So now, Shankar and I are going to provide a background deep dive on a couple of technologies, their limitations, and our vision of the future in each of those spaces. Over to Shankar.
Thank you, Alice. Well, I've been in Cambridge a while, and in Cambridge, we think about DNA quite a lot. And in the, could I have the slides back, please? Thank you. In the figure here, you'll see the double helix structure of DNA, which was solved by Watson and Crick in Cambridge in 1953. Now, DNA is fundamentally an information molecule, and that's going to be at the heart of what I'm going to talk to you about today. It is composed of a 4-letter code, G, C, T, and A, and the basis for the code shown to the right here is the fact that the letter G can communicate with the letter C, and the letter A can communicate with the letter T. And this pairing, called Watson-Crick base pairing, is what you see down the central stack of this double helix. Now, this is the molecular basis for what we call the genetic code, and it is fundamentally the code for all living systems. Now, I'm going to talk to you about the fact that we are going through a revolution in DNA at the moment. And on this slide is marked out 3 distinct dimensions in which we're seeing transformation. The first is reading the code which I've just described. This is often termed sequencing because it's about detecting the order in which these letters are arranged. And for example, in the human genome, there are 3.2 billion letters arranged in a particular way. Now, the technology for reading this code has become about 10 million times faster and cheaper over the last 2 decades. And it will get even faster and cheaper in the future. Now, this is driving the sequencing of human genomes on a population scale and beyond. And primarily at the moment, this is being used to transform the area of genomic medicine and personalized medicine. And it's having a major impact in the areas of oncology, rare genetic diseases, and infectious diseases, to name but a few. And we're really just at the early stages of this transformation. On the bottom left, continuing this analogy with the alphabet, is the word editing. It is now possible to go into cells and make precise changes to the letters of the genetic code via a collection of technologies that are referred to as genome editing. And we're at the very early phase of seeing what's possible here. Examples of applications will be the ability to re-engineer cells for cell-based therapies. On the bottom right is the word writing. The ability to synthesize genes and synthesize genomes is going to be transformed over the next 20 years. In fact, at the moment, this is lagging behind the ability to read. So we can read faster than we can write. But over the next 10, 20 years, the ability to write DNA code will be transformed. And this, amongst other things, will allow us to design and write genomes to order. Now, staying on this slide for a moment, I want to return to the idea of DNA as being fundamentally an information molecule. Now, it has been shown that you can actually store digital data in synthetic DNA sequence. In fact, a gram of DNA can store more than 200 million gigabytes of digital data. It's even been estimated that a shoebox of DNA could store everything that's ever happened in the history of our world. So therefore, DNA is arguably the most volume efficient way of storing digital information. Now, we have sequenced the genome of the woolly mammoth, and that demonstrates just how hard-wearing and long-term this method of storage will be. And as we improve our ability to write and read DNA cheaply and quickly, I believe DNA will become a method for digital information storage. And as we also adapt our ability to dynamically alter aspects of the coding features of DNA, it will also become a mechanism for dynamic information storage and perhaps processing. Now, on the next slide, I'm going to introduce yet another dimension of coding in DNA. I'm going to introduce the word epigenetics. I've described the primary code of DNA as being the ordering of the letters that go through the middle of that double helix. Now, you'll have noticed that the helix has two grooves. I'm going to draw your attention to a groove that was called the major groove. That's the larger of the two. Now, the major groove has features that project not inwards into the helix, but outwards. And these features are recognized, and in a sense, they are read and interpreted by machines in biology called proteins. And the way in which they interpret what they read in the major groove can determine whether genes are switched on or switched off or somewhere in between. Now, there are dynamic chemical changes that occur on the DNA letters that project into this major groove and present yet another dimensionality of information, and this is dynamic information. So this information layer is critical for determining the program that dictates how all the genes are collectively in a state of being active or inactive or in between. And this determines the overall characteristics of the cell or the state of the cell. Now, this is profoundly important when a stem cell differentiates into very specialized cells, for example, skin cells or heart cells, liver cells. Each of these cells has the same genome, but the epigenetic programming is different. They have different sets of genes in different states. So the epigenome is absolutely critical for defining states of cells. And if you change the epigenome, you have the capacity to reprogram cell states as well. Now, we have a portfolio company that has a technology for detecting these changes in DNA floating around in a blood sample. And at the moment, that's being used to detect early stages of cancer. So disease states also manifest in changes in this other informational layer called the epigenome. Now, in a moment, I'm going to hand over to Steve, because there are ways of manipulating the epigenome to alter cell characteristics. And Steve is going to tell you about a specific example where we've done it. I'm going to hand over to Steve.
Great, thanks, Shankar. It turns out that one of Aaron's other portfolio companies has developed an algorithm to determine the groups of transcription factors that bind to DNA and guide this genetic information, how these transcription factors are able to, through controlling genes, turn one cell type, say a fibroblast, into another cell type, such as a cardiomyocyte. Importantly, without the cell needing to transit through a so-called stem cell state. So it only takes a moment of reflection to realize how transformational this opportunity is. The ability to transform one cell type directly into another. This technology can now do in a matter of minutes what it's until now taken researchers years of trial and error to do. Now, this, of course, is fantastic science, but it's not just cutting edge technology, it's highly commercial. In the medical arena, for example, just one cell type, the cardiomyocyte, represents a multi-billion-dollar market. Furthermore, the same technology and approach can be applicable to other cells with therapeutic potential in a range of other areas. Just for example, in osteoarthritis, certain forms of blindness, and T-cell therapies. Now, the way this company arose provides a very interesting and I think great paradigm for the Aaron model. In this case, I came across a junior researcher at a conference who was talking very excitedly about his compelling ideas and data. And in parallel, it turned out that his discoveries had also come to the attention of Savanki Ramakrishnan, another Aran Science partner who's based at the MRC LMB in Cambridge. Now, out of our ensuing discussions with the entrepreneur, it became really clear to us that there was truly a very exciting opportunity here. And over the course of just a matter of months, I and others at Aran spent quite a lot of time with this scientist entrepreneur and his colleagues discussing the opportunities and helping shape the goals and the vision for a company. Now, in getting the company off the ground, I served as an interim chair of the board, I think, which helped steer the company in the right directions. And it's now wonderful to see this company thriving and growing. So this is how we work at Aran, and I think that kind of model provides a great paradigm for how we can measure other companies now and in the future.
Great, thank you, Steve. So now shifting gear a little bit. As most watching will know, the most significant breakthroughs in AI in recent years have come from a form of machine learning called deep learning. The following will be basic for a number watching, but to set the stage in order for us to then talk about limitations and opportunities going forward in the space, I wanted to explain the following. So a deep learning system learns to map some inputs, say pixels in an image, to some output, say labels for objects in the image. It's called deep because that mapping is composed of a number of layers. The way that it works is actually rather straightforward. Initially, the mapping from input to output is random, and the system makes many mistakes. But each time a mistake is made, the connections in the system are tuned ever so slightly, so it's less likely to make that same mistake again. Over time, and seeing millions of labeled examples, it learns to classify the majority correctly. Importantly, it also ends up generalizing, meaning that if you give it an image that was not in that initial training data set, it will correctly classify that too, so long as it's statistically similar to the others. But as we know, next slide please, deep learning has a number of important limitations. It requires massive data sets for training. It's essentially a black box, with the programmer even unsure why the results come out as they do, and it's easily tricked. In the now famous example, with the right tiny perturbation, we can get the images to be classified as anything we want. As we see here, this poor panda is being classified as a shark or a goldfish. The worst part of all of this is that the algorithm is confidently wrong. There are more subtle, potentially invidious social consequences too. For example, current predictive algorithms on social networks were in theory designed to provide the user with content they wanted, which was relevant to them. But if the objective function of the algorithm was in fact defined as maximize click-through revenue, that's actually a rather different thing. The corollary of this was that a few lines of reinforcement learning code actually changed the user's preferences, effectively changing the user. So where the standard model of AI seems to go wrong is that its success is based on the extent to which its outcomes meet its objectives and that there is a clear goal. But the reality is that we do not know how to properly define an objective, and it's this that can lead to unintended consequences. So moving on to solutions and investment opportunities. Beneficial AI is founded on the principle of building machines that, rather than using the typical Markov processes underlying reinforcement learning, are instead explicitly uncertain about their objective and indeed guaranteed to help with our actual preferences. The way it works centers around three tenets: altruism, solving the instrumental goal issue, where a machine will not enable itself to be turned off at all costs to meet its defined objectives; humility, being explicitly uncertain of what human preference is, obligating cooperation; and observation, the premise that the ultimate source of accurate information is observing human behavior rather than taking a literal interpretation of our poorly chosen words defining an objective. If we get this right, we can achieve the economic upside of AI without the societal cost. As our science partner Zubin Garamani explains, it has become fashionable to compare AI to human intelligence and to envisage Terminator-style AI robots. But we feel we should question this. The human brain and AI are very different. The brain is complex and remarkable, particularly its energy efficiency, able to run on the same energy as a 20-watt light bulb. However, the human brain stores very little information about the world, of the order of 2 terabytes, about the size of a hard drive. Also, we know from cognitive science, human reasoning sadly is flawed and our perception is limited. On many tasks, humans are much better than us already. What this tells us is that we should not think of the goal of AI as mimicking humans. Instead, we should move away from this human-centric view of AI to focus on the potential for AI to solve problems that humans are not good at, to complement human intelligence. This is a positive message. Examples include optimizing the transportation network of a city in real time, extracting patterns in biomedical data sets with millions of genomes, screening molecules for their therapeutic properties, or detecting fraud or harmful content online. This is what Aaron's focused on, and if we get this right, the opportunities are profound. Now, a brief glimpse further into the future. Aaron is working on automating machine learning using machine learning to create a system that is unbiased, does not require large data sets, and can explain its decision-making. We believe this could be transformational and has the potential to open up vast markets where previously AI was not allowed for regulatory reasons. Another breakthrough Aaron is working on is yearly charging. So if you shine a laser light at a microcavity, the atoms interact with the light, kicking off a quasi-particle, a polariton. These quantum particles are correlated. This means they spin and move in the same direction, properties of a superfluid at room temperature. If you use polaritons in this way in a transistor to store, switch, and send information, instead of using electrons, which constantly bump into each other, causing energy dissipation, you can create near zero energy loss. The commercial implication? You could charge your iPhone once a year, not once a day. I think a few of us might like that product. Today, encryption, securing messages, works by multiplying together a large number of prime factors to create a key. But as quantum computing progresses, this has the potential to be factorized, i.e. unentangled, in a split second. This means that everything encrypted on the internet, all of your banking details, every message you send, and every message you've ever sent, may become instantly available. At Aaron, we've invested in the company working on the solution using a fundamental property of physics, that if you have an entangled photon pair, measure the state of one photon, the state of the other changes, no matter how far away, even on the other side of the universe. They use this to send keys securely via satellite and enable unbreakable quantum encryption. We also have projects relating to manufacturing in space, bioengineering of trees to remove pollution from the air, contribute nutrients to the soil, and benefit the environment, animal cognition and communication, and design of cutting-edge immediate alert systems, including smart biological sensing of one's environment. Given the pertinence of this at this time of COVID-19, I'll say a few words on this one. Our vision is to create a genetic monitoring system to automatically and instantaneously detect whether there are pathogens in the air, preventing their spread. B, discover a virus endemic in animals, say birds, bats, or pigs, before it jumps into humans. And C, detect your immune response to such a pathogen, checking your autoantigens, what it is you're exposed to that causes you to become autoreactive in your immune response to the environment. Our vision is that it would be extremely fast, cheap, tiny, and integrated into a software to link to a network of many millions or billions of sensors worldwide, exchanging information within seconds. Ideally, we could invent non-invasive body sensors, enabling 24-hour monitoring. In sum, we believe a generational opportunity exists, and that's why AREN was founded. We empower and support exceptional entrepreneurs with exceptional technology to prosper, succeed, and change the world for the better. It doesn't feel right to talk today without acknowledging the situation we're in. The global scientific effort and collaboration has been tremendously impressive. I have confidence in our society to meet this challenge, and at AREN we have been deeply committed to playing our part. We do not think there's any quick solution to this problem. It may be many months before we achieve any sense of normality. However, it is not deterministic. We as a society will determine the outcome in our actions from now on. One must in no way diminish the terrible suffering of the moment, but I do feel, in relation to the pandemic at least, we must consider that we may have been spared an even greater tragedy this time, and must use this as a warning not to go back to our old lives unchanged. My great hope in all of this is that we can use this crisis to serve some positive purpose. I hope a shift from self-interest towards acting as a humanity will not only happen, but that it will continue once we've emerged from the other side. Perhaps we'll be able to use frameworks and connections without borders to tackle the other pressing needs with which we're faced, including true racial equality, not just nice words, preserving our precious planet, preparedness for any bioattacks, beneficial AI, and ensuring global food supply. While those perhaps used to sound like vague, faraway sounding words, I think for many they have now hit home. After all, what's the point of making money if we have no health? Why would we travel across the globe unnecessarily if we destroy the precious earth we live on? And who's going to be hoarding power if humans no longer exist? There are a few rare times when one is called to step up and work together for the benefit of humanity. This feels like one of those times. Let us all be able to look back and say, when it mattered, I played my part. And for those of you like us seeking to create the future using deep tech and deep science, I'd ask that you each ask yourselves, what can you do in all of this? What have you always dreamt of? What do you want to be remembered for? And how can we at AREN help you to achieve it? The collective energy, intellect, and talent of those watching is profound. Let's act together using that human endeavour and ingenuity of which we spoke at the start to achieve something of which we will all be deeply proud. Thank you. And that ends our session today. We weren't able to do the Q&A, but please feel free to connect with us, and hopefully that last slide will stay up so you'll know how to do so. A warm thank you to Sir Shankar and Steve for joining us as well today.
You're welcome.
Thank you very much, everyone, for that session. That was absolutely fascinating and such a brilliant way of kicking off the day. We're now going to have a little break before the next session on this stage, on the cutting edge stage. The next session is at 12 o'clock. and the title is going to be Privacy Preserving Machine Learning, Having Your Cake and Eating It. An interesting question that I think lots of people are going to be thinking about a lot over the last 2 days, but obviously continuing into today's programming across all of the stages. Speaking of all the stages, we have many different sessions still coming today. So many different speakers from so many different industries. So while you have a little break on this stage, go and have a little look at who else is speaking. Make sure you have a little look at the expo. There's also some networking rooms that you can get involved with, and of course you can join the conversation on Twitter and other social media channels using the hashtag. Thank you very much for now, and I'll see you again at 12. Hello, everybody. Welcome back to the cutting edge stage here at CogX. I hope you've been enjoying the morning already into lunchtime. Can you believe it? Or perhaps the second half of the day for others. Thank you so much for coming and joining this session. We are going to be focusing on privacy preserving machine learning, having your cake and eating it too. And you're going to have a familiar face in Libby Kinsey coming back to moderate this session. If you were here yesterday, you remember she moderated the brilliant session on planetary technologies. But yes, here we're going to be talking about privacy preserving machine learning and when it is useful. Just to remind you all, you can join the conversation on Twitter using the hashtag. This is a session that's going to have a Q&A session attached to it. So please do submit your questions in the Slido while the speakers are chatting, and of course later on in the Q&A too. But great to get your questions in whenever you're ready. And with that, I'll pass on to Libby. Enjoy the show.
Good afternoon. Thank you for joining us on the cutting edge stage at CogX this year. My name is Libby Kinsey. I am a technologist at Digital Catapult and an independent consultant and researcher. In this session called Privacy Preserving Machine Learning, Having Your Cake and Eating It, we're going to look at whether you can build effective machine learning models whilst protecting sensitive or private data. We're going to do it with 3 talks from our 3 guest speakers, and they'll cover applications, solutions and technologies, and then move into a discussion. So we want to try and tease out what are the current capabilities, the potential benefits and trade-offs of privacy preserving machine learning. So let's get started. Our first speaker is Oliver Smith. He is Strategy Director and Head of Ethics at Telefonica Alpha Health. And he'll be talking about the use cases for privacy preserving machine learning that he's looked at. Over to you, Oliver.
Thanks, Libby. It's great to be here, everyone. Good morning, good afternoon, wherever you are in the world. So having your cake and eating it, which is obviously what everyone's keen on. And in the line of work I'm in, that means can we create great digital healthcare that actually doesn't require any private data at all? So let's take a look at my presentation, and we'll go through a bit of background on Alpha, a little bit of why we think privacy preserving machine learning is important, and then finally what we've been looking at and what we think. So in terms of Alpha is part of Telefonica. So Telefonica is a global telecommunications company, and they set up Alpha back in 2016 as their disruptive innovation unit, their moonshot facility, as we call ourselves. And we're based here in Barcelona. That's our building, which I haven't been in for a long time now. But I'm in Alpha Health, and Alpha Health is focused on trying to really radically improve access to great healthcare and using digital technology to do that. Just to give you a little bit of context of that, we've got 4 products in our portfolio at the moment. The first of these is called Evermind, which is really about self-care, and it's focused on helping people with their stress. The second is Perspectives, which is digital cognitive behavioral therapy, and this one's unsupervised. So as you would imagine, it's going through clinical trial at the moment. It then has a sister application, which is called Mindset, which is actually for supervised digital cognitive behavioral therapy. So with this one, a doctor supports your care. And then finally, we have a product we're working on called Foresight, which is using data to actually predict whether someone would have a crisis. And of course, that then allows a clinician to do something about it, and so hopefully avoid that crisis. So the purpose of really showing you this is to, I hope, demonstrate that it's obvious that across all of this portfolio of mental health applications, they are applications that will require data if we're able to actually personalize and improve the product. And that's got us thinking about, well, wouldn't it be great if we could actually avoid sucking in lots of personal data and actually get to privacy preserving machine learning as part of what we do. So let me say a little bit more about how we see PPML and why we're doing it. There's lots of different technologies for privacy preserving machine learning. I'll go through a few of the ones we've looked at in a moment. But in terms of what we are looking for from it, we see it as it's the training and deployment of models without actually requiring access to any personal data, and crucially, without any detrimental impact on model performance or user experience. And this for us is but one part of actually what we're looking at in our ethics work. We also look at new design patterns, particularly thinking about consent. Yes, we look at technology that we want to embed into our products, and that includes privacy-preserving AI or machine learning, as well as explainable AI. And then finally, we also have an aspect of our ethical work, which is really about audit and governance. And we have external audit, and we use a company, again, based here in Barcelona called Eticas to do those audits. Hopefully you can't see that little pop-up. This is all underpinned by a framework of principles and commitments that we have. And the reason why we put so much effort into this is because we think that without this ethical approach, without building trust, we're just not going to have the impact that we want to have. We're not going to be able to improve access to great quality healthcare. Most people will think of this in terms of data access, and of course that is really important. If people don't trust us, then they're not going to give us access to their data, and therefore we won't be able to build great products. But it also affects other aspects. Effectiveness is a good example. Thinking of Evermind, for instance, there's a part of that product, it's journaling, where people write down their thoughts, and it's an important part of care. And of course, if you don't trust that data is going to be managed correctly, held privately, then you won't write down your thoughts openly, and you won't get the real benefit. So that's really why we've got into privacy preserving machine learning, and why we set up a team here in Alpha Health to look at that. And what we've been doing over the past year or so really is just exploring different technologies. So let me start. Oh, actually, no, sorry. Let me go through our goals for privacy preserving machine learning first. Obviously, we wanted to preserve privacy. Clearly, that's what we're going to want. But also, we want to be able to apply privacy preserving ML to both training and inference on a range of machine learning techniques. So not just say logarithmic regression, but also neural networks. As I mentioned earlier, we just don't want any worsening of performance versus non-PPML approaches. We don't want any worsening of user experience. So we don't want there to be lots of battery drain. If it's using lots of computational power on the mobile, that slows everything down. That's of course not great for users. We want to be able to protect our IP as a company, and ideally, we want it to be easy to implement. So okay, now let me go through some of those technologies. So I said we've looked at 6. Really struggled to try and get it down into a sentence each, but I think I've just about managed it. So of course, there's data anonymization. So you remove all personal data before machine learning is applied. There's differential privacy, adding a lot of noise to the data so that you're obfuscating it. There's secure multi-party computation, where you are randomly splitting the data into different parts, and then machine learning is applied on different servers, and then you bring it together. You've got homomorphic encryption, where you are applying the machine learning directly to the encrypted data. So you don't need to de-encrypt it before you do the machine learning. You've got secure enclaves, and for us in a mobile environment, that means on the phone there is hardware, there's a chip. We send our model to the chip, and the user's data from the phone goes into the chip as well. And it's all the machine learning happens there, and we can't see everything, and neither can the user see everything. And then finally, the technique I think a lot of people are familiar with is federated learning, where the model is sent to the edge. So for us, the model is sent to the mobile phone, and we're not receiving the data in the center. I know that Blaise and Hassan, who are going to be speaking a bit later, are going to say more about secure multi-party computation and federated learning. But in terms of what we were looking for, we try to assess in overall terms, what do we think is going to be right for us? And given those criteria that I went through earlier, what's going to be the best approach for us? So we created this chart. I have to say, Sebas in our team hates this, because he says this is just too high level. This doesn't do justice to the different the nuances. You're trying to look at a kind of general use case rather than kind of specific use cases. So he hates this, but the reason why I wanted to present this is because it for us, when we were looking at what we need for Alpha Health, we just thought, well, there isn't really a winner here. There isn't one technology that we just think, wow, if we just use this, then we can have privacy-preserving machine learning. I would say another couple of points on this is that this hasn't been updated with the latest on what IBM's just been doing on homomorphic encryption, and I know that the open mind community is working really hard on training on the edge from federated machine learning. This is an area that's moving all the time. And really that speaks to where we've got to, and we've decided that, well, firstly, we just need to explore a combination of techniques. I think we're going to have secure multi-party computation at the core. We'll bring in elements of others. But one aspect that we've learned as well that's really important is that it's super use case sensitive. And actually, my dream that I had that we could just take one technology and apply it to all of our use cases is not really right. And we should be being much more use case sensitive. Some of the companies that we've worked with, Duality on homomorphic encryption and Aphris on federated machine learning, and they've got some great technology, and I think they'd be perfect for specific use cases that we're developing. And so that's something we want to follow up as well, because we don't want the perfect to be the enemy of the good. And finally, we also just need to consider other aspects of our ethical approach. And one of the big debates we had on the team is explainable AI. And can you have XAI and PPAI together in the same product? We think probably not yet, but we think that is something that is going to be possible. So just to conclude, I think overall, sorry, Libby, but we still do need to choose between having or eating our cake. But it is changing fast, and we think we will see that we will be able to do those two things very soon. So that's the end of the presentation from me. Thank you very much, and back to Libby.
Thank you. Well, we can stop here. We've answered the question. No, thank you, Oliver. That was an absolutely perfect motivation for the why of privacy-preserving machine learning. We're now going to move on to Blaise Thompson. Blaise is CEO and founder of BitFount, which is a startup enabling companies to share data whilst maintaining privacy and control. Over to you, Blaise.
Thank you, Libby. Well, and I'm also very excited to be here on the stage and Cutting Edge, talking about privacy-preserving machine learning. I'm going to take a slightly different angle to Ollie and focus a little bit more around data sharing between companies. And so here, this is another area where I think privacy-preserving machine learning can be used. And I think it can be used for the better of all, because I actually think that there are a lot of cases where data sharing, in some sense, is very good. So if we can head over to my presentation, I'll run you through some of my thinking and then some of the things that we're doing at BitFount. So first off, why is data sharing a good thing, especially between companies? Well, I think there are many problems where the more data you have, the better a machine learning algorithm is. So this is one of many examples I've taken where people are building a classifier, and as the number of examples increases by a factor of 10, the metric that they're interested in this case, the average precision, keeps going up. And this has been seen in many cases. This is an object recognition task, but it's been seen in speech recognition, machine translation, and it seems almost that every machine learning task that we follow actually has this property. And I think this has very interesting implications for our economy. And so I want to talk a little bit about that in the context of companies and why they should be considering sharing some of their data. So first off, in any company, I think if you have a competitor company in the similar industry and you have some task that both of you have similar data for, if you're able to share those data sets, you would have an improvement in accuracy. And so I think that results in an immediate benefit for customers, where companies that do share parts of their data will be able to have better user experiences and better products. But I think that also comes to a second aspect, which has a big impact on economies, which is that if you have an industry where people aren't sharing data, then whoever's the market leader in that space has a very strong reinforcing effect where they'll become more and more a monopoly. So because they have the most data, they're likely to have the best product, and therefore users are likely to move towards them. And so I think that actually leads to another reason for companies to share data, which is if you're worried about the market leader in your space becoming a monopoly, then there's a really strong incentive for all the other companies in that space to share the data. Of course, there are big problems with sharing data, and they're really to do with privacy and control of the data. And I think what Libby's question is doing for us is asking, well, are there ways that we can share some of the benefits of data without risking this privacy and control? I think it's also worth spending a little bit of time thinking about what actually we mean by privacy. So people talk about a right to privacy, but actually that's something that's not necessarily agreed by everyone, that this should be a right. And even some very famous philosophers think that although we do want to have privacy, the right to privacy is really captured by many other rights that we think about. And so I want to talk a little bit about privacy in the context of freedom, which is another thing that we all care about and we believe we have a right to. And if my argument that that not sharing data has a risk of resulting in monopoly, then I think it actually means that being too careful about privacy without thinking about this aspect of its implications for monopoly has an important risk to our freedom. So I think there are really good political reasons as well as business reasons to think about ways that we can share at least the insights of data. Of course, it is true that we also don't want to risk what we consider important privacy aspects. And so that's where all these new technologies come in. So I wanted at some point in our three presentations to give a little bit of an insight into at least one of these at a more technical level, because I think some of these ideas are really elegant and very simple as well. So I want to explain in a little bit more detail how multi-party computation works at a high level. And so imagine now that you have two people, each of whom has a salary, which they want to keep private, but they are happy to have a third person work out the average salary. And so multi-party computation allows this to be done just by having person X and Y share a random number, which we'll call R. And then they each share something with the person in the middle. In this case, person X is sending X plus R, and person Y is sending Y minus R. And what's really neat in this is that now the controller in the center is able to calculate X plus Y just by adding these two numbers together. Because they don't know what R is, they're unable to work out what either X or Y is. And the result is that this person in the center, of course, has now been able to calculate the average salary. This is, as Ollie mentioned, just one of many new methods coming out, including adding noise, so differential privacy. Instead of agreeing a random number, the people would just add a random number themselves with zero mean. And then with enough samples, the controller would be able to calculate the average. And all these different techniques, I think they're actually conceptually quite simple, but result in really good guarantees on people's privacy. Of course, as Ollie mentioned, there are a lot of difficulties in implementing all of these things. And so that's why various different companies have been looking into ways that we could make this much easier. And so in my company, Bitfound, we've been focusing on building up a platform to make it easy and secure to share these kinds of data insights. Of course, because we're focusing on this business setting instead of in the case of individual users, we've realized that one of the important things is to build up trust. And so our approach has actually been to find individual domain partners for a specific area, and then build up a kind of a joint platform for particular domains. So one example of this is a really great company called Alpha. This is a slightly different Alpha from the one Ollie presented. You'll see there's an F instead of a PH. And they're the market leader in building asset finance software provided to many large companies. And so we're working with Alpha to bring this to the asset finance space, but also exploring other opportunities in other domains to look at applying this technology and these ideas in particular spaces. So I would actually say that from my perspective, I think there are aspects of the cake that we are able to eat while having it, but it's not so simple. And as Ollie says, we do need to be a little bit careful in the way that we do it. So I'll hand back to Libby, and thank you all for having me for this talk.
Thank you very much, Blaise. I'm going to move straight on to our next talk so that we can get into this discussion. Our final talk is from Hassan Mahmoud. He is Senior Technologist for AI and Machine Learning at Digital Catapult. And he's going to be talking about building a platform-independent demonstrator of federated learning. Over to you, Hassan.
Thanks, Libby. And like the rest, I'm really happy to be here. Shall we start my presentation? Okay, right, great. Okay, so let's get started. So, so in the next 10 minutes, I'll be talking about federated learning and how we can sort of develop platform-independent libraries and open ecosystem for it, and also about why exactly we'd want to sort of do those things. Okay, so like Libby said, I work at Digital Catapult, and Digital Catapult is a UK nonprofit with the goal of helping accelerate adoption of advanced technologies like AI, DLT, 5G by UK businesses. And within the AI team at Digital Catapult, one of the things that we are sort of interested in is ethical AI. And so federated learning is obviously a really great technology for doing privacy-preserving machine learning. And to that end, we sort of wanted to quickly build sort of a multi-device federated learning demonstrator for our clients. And one thing that we quickly realized is that it's actually much easier to sort of build one from scratch. So we explored the current frameworks that are available, and we realized that it's actually much easier to sort of build a library from scratch. And the experience of building this library and also sort of looking at the existing the frameworks that exist right now, it became really quickly clear to us that it's actually a really good idea to try to build and encourage people to build open source platform independent libraries and open ecosystems for federated learning. And the reason for that is because we believe that down the line, it will avoid fragmentation of the federated learning solution space, allow interoperability of the different solutions that people develop, help create a health ecosystem, which would allow for innovation and adoption of federated learning across the board, and possibly enable new kinds of business models that we haven't actually thought about right now, and give end users many choices. Yeah, so essentially everybody wins. Yeah, so then the question is, how do we actually go about building such open platforms, such open ecosystems? And the first step is to actually sort of tease out what's actually common to all federated learning systems. And once we do that, we can collaboratively define APIs and infrastructures that are common, and then implement the common core, and then sort of build on the common core, whether you're sort of actually developing commercial applications or doing research and experimentation. You start with the common core, and then you sort of build on top of that. So how do we actually tease out what's actually common between all federated learning systems? The way you can do that is by looking at such systems at a high level, and in particular looking at a federated training iteration, and then try to understand what's actually what the different dependencies are when you actually look at federated learning. Okay, so let's do that. So just to get started, this is what federated learning looks like at a high level. So you have a set of clients or a set of workers. So in this particular slide, I think you're seeing 3, but in general, it could be sort of millions. Yeah, so it can number millions, it can number hundreds, it can be yeah, it can be a lot. And so the idea is that each of these clients or workers have a local machine learning model, And they also have their own private data that they do not want to share with anyone else. And the goal within federated learning is to create a central global model at the server using the data from all the different workers, and but without actually looking at the data. So federated learning that's a goal of federated learning. So okay, so given that that's a goal, so let's look at how we actually sort of do that. So what I'm going to show you now are sort of five steps that you typically take during like a standard federated learning training iteration. Okay, so as a first step, the workers update their local machine learning models using the data they have available locally. Remember that this data is sort of private to each worker, and they don't actually want, and so the idea is to not share this private data. So as a first step, the machine learning, each of the workers train a local model based on the local data that they have, and the machine learning models could be quite different across the board. The second step, the workers send the local update that they did to their models to the central server. The server then aggregates the local updates into the global model. And after that, the server sends the model updates back to the worker. And finally, the worker then incorporates a global update into the local model. So those are the 5 steps in a typical federated learning training iteration. Now the question is, like, what are the dependencies in these instances? And what I'll show really right now in the following slides is that we can identify 3 different kinds of dependencies in a system like this. The first dependency is a dependency on the application. For instance, whether you're doing federated learning in medicine or in finance or in manufacturing, whatever the application might be. The second dependency we'll see will be on the actual federated learning algorithm you're using. And the third is sort of, we'll see that there are components, there are bits, there are sort of parts of the system that are actually common across all federated learning systems. And we want to sort of tease out what this, which parts of the system are what the dependencies are. Right. So let's look. So we go back to the iteration. So in the first step, when the local models are the workers are updating their local models in the local data. So that bit depends on the specific application that you're using. In the second step, when the workers send their updates to the server, the actual type of the message is sent. They're common across all federated learning systems. So this message type is other sort of actual sort of binary strings that are sort of that are model updates, or messages related to worker authentication and so on. But the actual content of the messages that exchange sent from the worker to the server, that actually depends on the federated learning algorithm. When the server aggregates local updates into the global model, that depends only on the algorithm itself. And again, when the server sends back the updates to the workers, the message type is common across all federated learning systems, but the actual message content depends on the actual federated learning algorithm. And finally, when the workers incorporate the global update back to the model, into the local model, that's again depends on the federated learning algorithm. So looking at this, so like I said, there are 3 kinds of dependencies we can identify, and this immediately suggests adopting a sort of layered architecture for federated learning, where at the bottom layer you have the communication backend, which is like a scalable API that handles the exchange of standard federated learning messages in a secure manner. And on top of that, you have the algorithm layer that sort of uses the primitives provided by the backend to implement specific algorithms. And finally, you have the application layer that uses the algorithm layer for specific applications. So the idea is that the communication layer is sort of common across all different federated learning systems. We can actually sort of collectively or collaboratively sort of define what the APIs are, what the requirements are, what the requirements are, and sort of build that collectively and define like a standard API for that. And then people are sort of free to sort of implement the algorithms or application layer however they want, or maybe there is an ecosystem of different kinds of algorithms and so on. Yeah. So at this, I think I mentioned in the beginning that we actually built like a library ourselves, like a proof of concept library, and that's called DC Federated. So yeah, so this library actually illustrates all the concepts in like a really small proof of concept library. And our current library, it's we don't really we haven't really looked into the scalability aspect too much, or the security aspect too much, because it's just a proof of concept that we created for our demonstrator. And yeah, so you can probably run maybe 10 to 20 workers without any problem, and sort of you can implement whatever algorithm you want, use it for whatever application you want, no problem at all. So given this sort of given this separation of between three, given that now that we've identified these three different sort of layers that we can divide a federated learning system into, it's worth actually looking at some of the current frameworks that exist and sort of see where they fit in. So what I've done here is I've chosen sort of 4 frameworks that are sort of representative, and we can already see that the fragmentation that I mentioned at the beginning, that's already starting to happen. So yeah, they're all sort of you can't really sort of use them with each other, and they don't really interoperate, which seems like which will likely cause sort of problems down the line. Yeah, so let's look at like how this sort of 4 frameworks fit into the framework that we just identified, into the sort of yeah, the layered architecture we just identified. So TF federated and PySwift are sort of respectively built mainly for TensorFlow and PyTorch, and so the application and algorithm layer are sort of built around TensorFlow and PyTorch, and the communication backend layer it doesn't exist right now for them because they're sort of they only mainly support sort of simulations. So, but my understanding is that these are sort of in the works. So hopefully they'll be implemented in the future. So the other 2 ones, like Fate, which is from WeBank, it's like a fairly large API, but the API is and my understanding is that it's mainly one of the major applications that we look at is finance. And so the stack that they have is sort of specific to sort of Fate, the application layer, algorithm layer, API that they have, and the communication backend layer is sort of stack specific to Fate. And Clara, which was developed by NVIDIA mainly for medical applications, again, so they have like the application layer and algorithm layer APIs are sort of Clara specific, and they have the Clara stack for the communication backend. And in contrast, so the little proof of concept library that we have, so that's sort of you can use any application or algorithm, whatever you want, but they are sort of all built on the sort of common communication backend primitives that are created in the core part of the library. And okay, so that's where you're at. So what are the possible next steps? So I think as a community, so I think the position we're at right now, so we can see like lots and lots of startups and people are sort of entering the space, like tremendous amount of research going on. So I think it's a great time to actually sort of as a community sort of figure out what are the common cores that are sort of common across everything, and sort of try to build an open, secure, scalable core that can be trusted by everybody, and not just for research, but also for sort of deployment as well. And so obviously we need to do additional research into trying to understand what is actually common across all these different systems, and so that we actually we have the right sort of infrastructure in place. And yeah, and it's also would be sort of like a great idea to actually explore what kind of potential new business models is made possible like this. So one really nice example is like a federated learning marketplace, where a client or a worker can choose which federated learning system it chooses to participate in based on financial incentives provided or privacy guarantees provided. Yeah, so if you have an open sort of infrastructure, it becomes a much more interesting and place. Okay, so what are the next steps at Digital Catapult in terms of federated learning? So of course, like we're going to sort of continue to sort of help our clients adapt federated learning if that's actually appropriate for their use case, and we're going to keep and we also want to extend the library that you have and build in sort of secure and the security and scalable components that are missing right now, and also open source that. So that's in the quite soon. We hope to do that. And also, we're going to be sort of investigating additional open source projects because we don't want to reinvent the wheel, obviously. So we're going to be investigating sort of open source projects that we can collaborate with or build on or extend. Yeah, that's it for me. And thank you, everybody. Thank you for listening, and I hope that was useful and you enjoyed it. And yeah, thank you.
Thank you, Hassan. And I'm going to welcome Blaise and Ollie back onto the screen because we're going to move straight on to the discussion now. And I'm going to start right at the top. So, Ollie, in your presentation, you had quite a shopping list of what you want out of privacy-preserving machine learning. And no surprise, right at the top was that it preserves privacy. Can we examine whether it's actually possible for machine learning to ever be perfectly private?
Yeah, I mean, from everything that we've talked to quite a few people on this and a few different companies, and we do think that it is. And I think actually one of the strengths of all of the techniques is that they hold the promise of being able to almost mathematically say, like, this is definitely private and we can prove it. And I think that that's actually going to be really necessary to help move a lot of these technologies on. Because if you think about anonymization at the moment, one of the challenges with anonymization is you can take a particular data set and say, well, this is anonymized, this is great. But then as soon as you're adding more data to it, it's you can break that anonymization, and so you're never quite sure, well, is it anonymous in this moment, or maybe not, or maybe we add this in, maybe it isn't. And I think that's where we need to get to, that position where we can say, no, we know, we can provably say that this is private. And I think all the different technologies hold that promise in their different ways. And I mean, I imagine that Blaise and Hassan can say more about this from a technical perspective, but certainly from looking across all of them, I do think it's possible.
Is that true? Is it true in theory, but not in practice, or not even true in theory? Blaise, do you want to speak to that?
Yeah, I think I would say it depends a little bit on what you mean by private. I think so. One of the ideas of privacy, which probably has the strongest guarantee, is the one that's called differential privacy, and that has this idea that you don't lose very much by being part of a data set. This is because a data set will always convey some kind of general ideas of behavior. So, for example, if in general people with blonde hair, are more likely to buy something than something else, then that is just an inherent part of the data set. And so you are losing you are providing some information by giving a data set away with that property. What differential privacy tells you is that by you being part of that data set, it's not very significantly different information that people that are recipients are getting. So I would say that's actually a pretty good definition of privacy, and it's quite a strong guarantee for people. In practice, a lot of people have struggled to get very useful models and information when using differential privacy. So along with the very strong guarantee of privacy, it does also come with, in some cases, a very strong reduction in the performance of the models. That obviously depends on the amounts of data that are around. But I think there are aspects of privacy that are actually guaranteeable. But I think it sort of comes down to what exactly you want by having this idea of privacy.
It's a good point. Let's not get into definitions of privacy here, because that could be a rabbit hole from which we never emerge. So I'm just going to pass on to Hassan and ask him, in federated learning particularly, whether malicious attack can be detrimental to your privacy there.
Definitely. So malicious attack can have sort of so in federated learning, so you're just not interested in preserving privacy. So that's definitely something that you're interested in. And so malicious. I think the main motivation for federated learning is that you're not actually sending the data; you're sending the model, which is sort of a distillation of what was contained in the data. And so you have that sort of first line of defense built into the whole sort of motivation of the system, but at the same time, it turns out that you can actually extract, in certain cases, you can extract, a clever person might be able to extract useful information about what kind of data a particular client was servicing. So, so in that instance, so like Blaise was saying, you can actually use differential privacy techniques at the individual workers, as an example, to make sure that the model updates that you send to the server are sort of protected. But that's not foolproof. It turns out that even with that kind of system, there are cases where whether there's like a malicious actor who sort of either maybe the malicious actor has infiltrated the central server, or the malicious actor is like a man in the middle. They might still be able to glean some kind of information from there. So right at this point in time, it's still an open question as to. So there are sort of lots of privacy. You can sort of you can sort of guarantee to some extent that it won't be sort of completely sort of all your data won't be completely exposed. But at the same time, it's an open question as to what extent you're actually protected. So just to answer your question, yeah, it's sort of yeah, there's always a compromise. It's not like a full.
The devil is in the detail. I could.
Yeah, exactly.
Right.
Yeah, I think the best thing is to actually you need to build trust the server. I think so. I think that's like a best case scenario. So if you can trust the server, you can sort of protect against other things. Yeah.
Let's move on to trade-offs. So we know that there are trade-offs in most methods for privacy-preserving machine learning. They might relate to energy usage or complexity or many other things. I'd like to cover all of those if we can, but first I wanted to go to Oliver and talk about maybe in the ethical realm, there might be some conflicts between desirable properties that we want from a machine learning system. So you talked about explainability and fairness, but you also said, I think, that you thought that these problems might be solved or will be solved in the future. Can you speak a bit more to that?
Yeah, so I think that some of them might be solved. And as we talk to a few different researchers, particularly on explainable AI and privacy-preserving AI, that there was a sense in which actually we do think we can bring these together. Where I think it's more challenging just to kind of stick with the fact that there are still trade-offs is say with bias. Actually, I think bias is a great example where you need to have actually a degree of personal data because you need to be able to understand whether you are looking at a particular group or not. We actually had this experience with a previous version of Evermind, a prototype or remix, where we didn't collect any personal data. It was great. We thought we'd done a fantastic job of data minimization. And then when our auditors, our external auditors at Etikas came and were looking at bias in the model, they said, well, of course, you haven't got any data. You don't know whether this is biased against women or particular groups because you just don't have any data on this. And of course, it's one of those moments where you say, oh, yes, that is really obvious now you've said that. And hopefully they were able to do some indirect analysis. But in that instance, actually, you could have a great privacy-preserving AI, but then you'd still be potentially stymied if you just didn't know anything about who you were serving. And you might end up in a situation where you'd say, what we should do is basically recruit a representative group of our customers to actually gather some of their data that they consent to for the purposes of understanding bias. And only that. So we're not trying to use the personal data for anything else, but you're using it for that purpose. So I think there are some areas where I believe we're probably never going to be able to get away from those trade-offs, but there are others where technically there might be some solutions.
Blaise, do you have any thoughts on trade-offs?
Yeah, I think there are so many trade-offs as soon as you get into all these ideas around ethics and privacy-preserving machine learning. So there are trade-offs between accuracy and privacy. That's a very classic one. And differential privacy actually has a very mathematical way of defining this. So there are two variables that you're allowed to change with differential privacy, and they each have impacts on accuracy. Within ethics, there are different ideas of what fairness is, and there are trade-offs there as well. There's a very nice paper sort of talking about different ideas of fairness, each of which we would all kind of agree with, and then proves mathematically that they're impossible to achieve simultaneously, except in very special cases. So I think there are many trade-offs in this space. As soon as you start bringing in ideas around ethics, of which privacy is really just one of them, I would say, there are endless trade-offs to be had. Actually, in some ideas of fairness also have a trade-off against accuracy, actually.
Yeah.
So,
it's
yeah.
multiple objectives to optimize over.
Mm.
Hassan, is in federated learning, can you achieve the same accuracy in a distributed way than you could if you had all of the data centrally?
No, that's probably not. No, I don't think so, because because you don't have the data at the central location, and you're sort of updating periodically, and so I think one of the things that happens in federated learning is that when you're actually sort of getting all the updates together, you're not getting the updates from all the workers. You're only selecting a subset of the workers and then getting the update from them. And additionally, the data distribution across the different workers are likely to be quite different as well. So you have these two different things that are sort of quite different. You're not using all the data, and you're getting sort of and the updates that you're getting for the different models are sort of biased towards those data sets. So so it's unlikely that you're going to get a model that's as good as if you had all the data in the same location. So but in terms of sort of the bias issue, I think so the fact that you're actually using only a subset of the workers to create the model, that also actually introduces a massive amount of sort of scope to sort of that introduces a lot of places where sort of bias can seep into your model, both because you're sort of selecting a subset of the workers to do the update, and because and so the workers you choose to actually update with will actually sort of change what model you're actually using. And also, for instance, if you're only updating using models using sort of devices that are sort of plugged in at night in North America, then the model that you create will be biased towards the data that's coming from that location. Because of the very distributed nature of the thing, it's really sort of there are lots of ways sort of bias can seep in.
Thanks, Hassan.
Yeah, no worries.
I think we only really have time for one more question, and I hope that this discussion has encouraged all of the people watching to join us for the Q&A, because there's so much more that we can cover. So I'm going to conclude with this one question, and it's to ask if any of the panelists know, are there good examples of privacy-preserving machine learning in the wild?
Well, I can start with that. I think there are very good examples in both Apple and Google, where both of those companies use privacy-preserving machine learning to build keyboard language models. So predicting what you're going to type, and both of them have been quite public about trying to push the ideas of privacy-preserving machine learning. Of course, they're both companies with very very large data sets and unusually direct access to people's phones. So I think there are some examples of this in practice. I think that there's a huge amount of interest in bringing it to the more broad ecosystem, but I wouldn't say there are that many examples publicly, at least, of people using it outside of Google and Apple.
Hassan, Ollie, anything to add there?
I think that there's not many kind of big kind of headline examples that you can point to. I think there's this really amazing ecosystem that's been developing now in recent years, and there's lots of, I think, good good examples emerging. I mean, actually, the work that Blaze is doing is great in finance. I know that people we work with in Duality and Aphoris are also doing good work where they're applying it to specific use cases. And actually, health is a great use case when you're looking at data across hospitals, which I think is simpler than the mobile use case that we have for our work. So I think they're starting to emerge, and really reflecting what we found, that they tend to be quite use case dependent in terms of the particular technology they end up using.
Okay, great. I'm going to wrap up here. I'm just going to say, come and join us for the Q&A. There are so many things we haven't covered. We haven't covered innovation in business models. We haven't covered the resources and tools that are available if you're interested in finding out more, or what is the trade-off about doing things openly as opposed to closed systems. All of these things we can cover in the next hour. I'd like to thank our three speakers. You've been wonderful. Thank you, Hassan, Ollie, and Blaze. And hopefully we'll see you all in 5 or 10 minutes.
Thank you.
Thank you, Libby, and all of your guests for that absolutely incredible session. So much depth there, and I echo what Libby said at the end there. For anyone who's watching, make sure you do go and dive into the Q&A session. It's going to be starting at 1 o'clock in 8 minutes time, or well, maybe it's not 1 o'clock depending on where you're watching on in the world, but here in London it's 1 o'clock, and that'll be for half an hour. So do make sure you jump over to that Q&A session, both to ask your questions, but also, as I say, continue the conversation that we've already had for the last 50 minutes. We're going to also have a break on this stage if you're staying here at Cutting Edge. The next session is at 3 o'clock, and it is called From Making a Prediction to Making a Decision, Why Causality Matters. So again, another really interesting topic of discussion here in the Cutting Edge stage. If you're not going to the Q&A with Libby and team, go and get yourself some food, or go and check out some of the other stages. There's the expos as well. There's also plenty of rooms for networking. And of course, you can join the conversation online using the hashtag. So enjoy whatever your next step is, and we'll see you back here in the Cutting Edge stage at 3 o'clock. Thank you very much. Hello everyone, welcome back to the cutting edge stage at Cognition X. I hope you've been enjoying the day, seeing lots of different talks, going and chatting to some fellow attendees and possibly speakers in some of the networking sessions, and of course visiting the expo. We're here for this next session, but of course there's still plenty of time today to do all of that and continue the conversation online using the hashtags on Twitter and all these sorts of places. But for now, we're here for the next session. This one's called From Making a Prediction to Making a Decision, Why Causality Matters. I'm excited for this session. Looks like we've got two amazing speakers and a brilliant moderator, speaking of whom it's Libby Kinsey again, who you guys will probably already be familiar with from previous sessions here on the cutting edge stage. So with that, I'll pass over to Libby. Enjoy the show.
Hello, thank you so much for joining us on the cutting edge stage. My name's Libby Kinsey. I am an independent researcher and consultant, and I'm a technologist in AI and machine learning at Digital Catapult here in the UK. This session is about research frontiers. We like to do some sessions on research frontiers on the cutting edge stage, and in particular, it's about causality in machine learning. In a recent paper by Bernard Skolkopf in 2019 called Causality for Machine Learning, he wrote that the hard open problems of machine learning and AI are intrinsically related to causality. And that's why we wanted to take a look at it here. We've got two keynote speakers, Rosemary and Carla. They're both experts on causal learning, but their routes to it and their domains of research differ. So it'd be really interesting to get their two perspectives. And when they've given their presentations, we're going to delve a bit further into why causality matters and what needs to happen to integrate causality with machine learning. Let's get started. First up, we have Carla Diaz-Ordaz. She is Associate Professor of Biostatistics at the London School of Hygiene and Tropical Medicine. And her research focus is causal machine learning in health. Over to you, Carla.
Thank you, Libby. Nice. So hopefully you can see my slides. There we go. So there we go. So the topic of this talk, of my first sort of like provocation, let's say, is so why causality matters. So I see this as a kind of like a two-way street. So I came, as Libby suggested, I come from the statistical causal inference academic world, where we know that causality matters. But perhaps what we have traditionally ignored was the use of data-driven algorithms that could help us go beyond our linear regression, for example. So my first foray into machine learning was how could I use machine learning to sort of like harness the information that was hidden in my data to make data-driven causal decision support a reality. And that's what most of this talk is going to be about. I'm going to touch towards the end a little bit of why machine learning needs causal inference to help make the learning that we get from our algorithms more robust, in the sense of tackling the lack of generalizability that we tend to see in our prediction models. So what this talk is not about is about methods for learning causal structure from the data, because I come from the traditional school of thought that correlation is not causation. But this is also a little bit of a provocation, perhaps, for Rosemary's talk. Right. So I want to give better decision support tools for sort of like scientists that consult with us as to how can we use our data to take better decisions. So what we have traditionally done in the machine learning world is to apply my best algorithm and then convert data inputs into predictions. So perhaps for a new observation for my next customer, I want to predict their purchases. And in my background, I work in public health. So perhaps it's more common to think of, for the next patient, what should be the medical treatment that I decide for this next person. But I want to start this talk by asking us, but is that really what we want? So there's been a recent discussion in the world of data science about the different goals that we have as data scientists. Professor Miguel Hernan from the Public Health School in Harvard recently wrote in 2019 a paper where he roughly says that goals are divided into descriptions, sort of like correlations between the data, features, prediction, and counterfactual, so what we're going to call causality. And this roughly sort of is equivalent to Yuda Pearl's ladder of causality, where he says the lower rung of questions we can ask and answer from data is association, again, correlation between our features. Intervention, what happens if I take an action right now, what would be my outcome, which is already a causal question. And counterfactual, which in Yuda Pearl's world is kind of something that contrary to fact, perhaps saying what would have been my salary now have I been born a man, for example, right? So I say that whatever we do as data scientists, we need to understand the aim that we are trying to achieve and then select our analysis and our algorithms which are best aligned to that goal. So let's start with a little example, sort of like a toy example, somewhat inspired by the COVID-19 crisis. So let's say that I have patient data from pneumonia patients that present at hospital for admission. And then we have lots of characteristics measured from them. So their age, weight, dietary habits, whether they have other heart conditions, asthma, lots of things. As rich a set of covariates as you want. And then my clinician collaborators ask questions. So perhaps they want to know, what is the risk of 30-day mortality for these patients? This would be a prediction model. But maybe more importantly, they also want to know, what would be the risk of mortality if I were to admit them to the ICU? Or perhaps, should I give ventilation to any one individual? So you can see that these three questions are very different in flavor. And I'm going to convince you that the last two are causal questions and that simple prediction algorithms are not going to be adequate to give the clinician the tools they need to help them decide what's the best course of action for the next patient. And in particular, choosing treatments requires both causal thinking and prediction. So let's continue with this little example. So just to introduce the concepts of causality, imagine that I have this one patient who is age 74, male, and I have all their characteristics there. And then I want to know, if I admit them to the ICU, which I'm going to denote here by A, your treatment is equal to 1, what's going to happen with your outcome, right? What would be your outcome if I admit you to the ICU? And in this example, I'm saying that your potential outcome, which is denoted by a super index 1, is this person is going to be healthy and discharged from hospital at 30 days. Now, what would have been the outcome if instead of admitted to the ICU, he's given treatment 0, so not admitted to the ICU. And in this example, I've decided that this person is still going to be sick and hospitalized. Now, this is all the ingredients I need to do causal inference, because what I want is the contrast between these two potential outcomes, and that would be the treatment effect of getting admitted to the ICU. Unfortunately, we only get to observe one of these outcomes, because for any given person, I either admit them or not admit them to the ICU, and these decisions are not taken at random. So the treating clinician decides, given their knowledge and your characteristics, what to do. So in the real world, where I don't have all this perfect information, what do I do? And this is why the causal inference literature has developed a set of assumptions that are at least sufficient to be able to make progress with observed data. So, so the ground truth will remain unknown. I'm never going to be able to observe both of these potential outcomes. So I have all your characteristics. They're simultaneously associated with your outcome, whether you're healthy or not healthy, and also whether you end up getting the treatment or not. And so if I want to estimate the causal effect of this treatment, I'm going to need to make assumptions to make progress. And, I don't want to get too technical, but we can just quickly say what these assumptions are. And so if basically I think if I measure enough characteristics of these patients so that I can imagine that there is no extra association between the treatment that you get and your potential outcomes, given all these characteristics I'm adjusting for, which is known as conditional exchangeability, then I can use data from the people that did get the treatment to sort of like estimate your potential outcome. This means that also the treated and the untreated must be similar in the sense of having roughly probabilities that are getting any treatment, so either getting the treatment or not getting the treatment. And under these technical conditions, I can actually use data to estimate this causal quantity at what would have been your predicted outcome have I taken this action. And so I can use this to formulate a type of treatment effect that is not your individual treatment effect, because that was impossible, but a conditional average treatment effect, where I'm kind of using people that are like you in terms of those measured characteristics L. So now this can be used to decide a policy or a treatment recommendation. So roughly, if this quantity here is, for example, positive, I can say, oh, okay, so the treatment has a positive effect on this patient, and therefore I'm going to treat. Or I could say, well, I want it to be sufficiently bigger than 0 because maybe it has some side effects, right? If it is something like aggressive ventilation, and I can put this lambda parameter to sort of make sure that the benefit really offsets perhaps the adverse effects of the treatment. And also, in statistics, usually we want to know that this effect is really there, and it's not just sort of like by chance findings. So we usually would have a measure of uncertainty around these numbers, and I would want that the whole of the plausible values of my average treatment effect are way above the threshold before I recommend my system to recommend the treatment. So that's your sort of causal inference in a quick whirlwind. So where does machine learning enters in my world? So this has been all traditional causal inference. So now, up until recently, people have been using just simple models to estimate these conditional expectations. But more recently, we have been using sort of machine learning algorithms. And here is two caveats that where the two worlds collide, right? So the one naive implementation of machine learning methods would be to just sort of use my favorite predictive model for predicting the outcomes given treatment and the characteristics, and just plug it into this estimator. But it turns out that this actually results in large approximation bias, partly as a result of the tuning in process, and is much more damaging in small samples. But it's also quite difficult to calculate the uncertainty around these numbers. And as I say, if I want to recommend the clinician a system that they can trust, it is important that we understand the uncertainty around these estimators. So without wanting to give you too much detail, the way in which machine learning algorithms are brought into the causal inference world is important. So if I just want to use them for prediction, then I'm quite happy with just using, say, the machine learning algorithm directly. And perhaps I can do a smart tweak, which is to optimize my algorithm to minimize the mean square error, as opposed to just the raw outcome. But for decision making, it's important that I do it in a clever way. And for this, statistical asymptotic theory, funnily enough, is important. But that's like a topic for a different conversation. So I just wanted to quickly show you a little example of how ignoring causality can go really wrong. So this is an old example. Some people use a machine learning predictive model for mortality. And they were going to use this to triage, to decide whether to admit patients to the ICU, to the intensive care unit. So when they deployed their predictive model, they found that asthma patients with pneumonia seemed to be less likely to die, which kind of started the bells ringing, right? Because this is sort of dangerous, and kind of it went against what was expected. And so what went wrong there is that the model should have been a causal model. And they should have set it up as in what would have been the risk of mortality if the patient were or were not admitted to the ICU, and they didn't do this. And the things went even worse in a way, because in the training data, the treated and the untreated were not similar. So in particular, it was found that in the training data, there was a sort of policy that most asthmatics were immediately transferred to the ICU. But because the ICU wasn't in the model, it appeared as if the asthmatics were sort of getting healthier, right? So this has been now noted in the literature. And so if you have this type of covariance shift between your training and your deployment set, causality is actually more difficult to achieve, and we have to pay attention to these things. And this has to do with generalizability. So this is my last sort of like slide. And I just wanted to end up by saying, well, causality is actually hard, but I don't want us to stop doing it. I want us to start trying harder, especially in topics like health, because we must remember, to quote one of my mentors, Nick Jewell, that every data point is actually a human story, and I think we should actually sort of respect the people that we're analyzing and sort of give our best effort, right? So this was my last slide, and over to you, Libby.
Thank you, Carla, for those informative slides and that provocation, I suppose I should say as well. Our next speaker is Rosemary Kerr. She is a PhD candidate at MILA, the Montreal Institute of Learning Algorithms, where she researches causal learning and model-based reinforcement learning, and is, I think, answering or trying to answer some of those questions that Carla raised. Over to you, Rosemary.
Hi, thanks. Hi, I'm Rosemary. I will be giving a talk today on causality and deep learning. I'm a PhD student at MILA. Where I mostly work on deep learning and causal learning and some credit assignment and so on and so forth. So I'll start off by just giving a really quick brief on what is machine learning. So deep learning, it's a machine learning algorithm. Essentially, it's one way to do machine learning. And machine learning is basically a discipline where we want to learn rules or patterns or algorithms to do a certain task. So imagine that if you have an autonomous driving car, you want the car to drive from point A to point B. You don't want to set out all the possible rules that the car has to follow. You want the car to be able to learn traffic rules, to watch out for pedestrians, to watch out for other cars, to follow, to be able to get from point A to point B. And this is opposed to, for example, things like accounting, where if you're given a task, you're given the context, you're given the person, you know exactly what you have to do. You don't have to learn the rules, you just have to follow the rules. And this is similar to arithmetics and many other disciplines. And what are the ways that you can learn those rules? So there are essentially like two main ways that you can learn it. So you can either use some type of a heuristic, or you can learn it from data. So what I mean by using heuristics are, okay, so those are two images from ImageNet. And imagine you have to do image recognition. So I give you this image and you have to tell me, your model has to tell me what is in the image. So for example, on the right-hand side, we have a car, on the left-hand side, we have a bottle. If I was to give the model a heuristic, I can say, well, if I see something that's like a rectangular shape, like a box-looking shape, and has some wheels, has a window, it's likely that it's a car. And if I see a cylinder with, a cap, something on the top, it's likely that this is a bottle. So this is an example of giving heuristics to your model. Another example is I can just give those image. I can give those image to your model, and I don't tell your model exactly how to recognize what is in the image, but I just tell the model that, okay, so the first image is a bottle and the second image is a car, and the model will have to learn from data what makes it a car and what makes it a bottle. And recently, there's been a lot of talks about, in the past few years, there's been a lot of talks about big data. So big data just means we have a lot of data, at least a lot more data than we used to have. How does this impact machine learning? So when we have a lot of data, learning actually becomes more effective. So learning from data becomes more effective. And learning, defining the heuristics it actually becomes more difficult. So I'll give a simple example. So these are still images from ImageNet. So it's a very popular computer vision data set. So they're all categorized into like different categories, and these are images of dogs. So if I was asked if I was asking someone to come up with heuristics for a dog, you'll probably think of, a furry animal that walks on 4 legs, that has a tail and an ear. And so this is great, and that fits the criteria of the first 2 images that we see on the left. But then you might see an image on the right, which is, a dog wearing a hat, but you haven't seen the hat before. You haven't defined the heuristic for a hat. And then the model wouldn't know what to do with it. The model would say, I don't know what it is. So if you were, so this is an example of if you were to hand define a heuristic for every possibility, and when the data grows, when you have a lot of data, this becomes exponentially more difficult. It's actually a lot more efficient if I just give all of these images to the model and ask the model to learn what makes a dog a dog. And I would say all of these are dogs, and the model will just hopefully naturally learn what makes a dog a dog. So this all sounds great, right? So this all sounds great. What could go wrong? So what can go wrong is that we don't have infinite data in infinite time and infinite compute power. So it's true that we have a lot more data than we used to have, but we still have limited data. So what does this mean? This means that the model that we've trained our model on, which is training data, it's not necessarily the model we've tested the model on, which is test data. So imagine if you train up a robot with some data, and now you release the robot in the real world. The robot will see different data than the ones that you presented it. And we want the model to basically generalize to test data as well as training data. And this is not a trivial task. So this is an example here of why this is not trivial, which we'll also get back to later on. So if you see, this is essentially another image recognition a task. So on I want to recognize if the person is playing a musical instrument. On the left-hand side, that's fine. I have a person, their arms are kind of in like the right angle, and they have some kind of object in front of them, and the model recognizes the person as playing instrument. And then the model look at the picture on the far right and says, okay, well, the person's left arm is sort of in the same angle as the other 2 pictures, and he has some kind of an object in front of him, so he must also be playing instruments. But any human who's seeing this would know that this is wrong. The person is not playing instrument, they're fixing a bike. So what went wrong? So what went wrong is the model didn't learn to, the model mixed up correlation with causation. So what do I mean by correlation? So correlation are things that happens together but does not cause each other. I'll give a quick example of what it actually means and what other things does it entail in machine learning. So for example, you log on to Amazon, right? So you bought a laptop, and then Amazon recommended you and says, well, why don't you buy a laptop bag with your laptop? And this is great. I've spent like $2,000 on a laptop. I can spend $30 or $50 on a laptop bag. So when Amazon looks at this data, they see, okay, well, laptop also almost always goes with laptop bag. This is great. But now what if you also logged on to Amazon and you bought a laptop bag, and if Amazon recommended a laptop to you, you probably won't buy the laptop. That's because your laptop, the act of you buying a laptop bag is mostly caused by you buying a laptop, not the other way around. So correlation means that buying a laptop and buying a laptop bag usually happens together. But causation means you also have to define the arrow that goes one way or another. So if 2 things happen together, there are basically 3 possibilities. It's either buying a laptop causes you to buy the bag, or you buying the bag causes you to buy the laptop, or there's another variable X, which we're not observing, that's causing you to buy the laptop and buying the laptop bag. So basically, causal discovery means we have to figure out the graph, the underlying graph, and which way the arrow goes and what the relationships are. So these essentially causal models, and Carla has already defined it in her talk as well. So what does a causal model allow you to do? So a causal model allows you to answer interventional questions and counterfactual questions. So what do they mean? What do I mean by that? So as you can see, we have like a very simple causal model on the right hand side. If I was to perform an intervention, that means if I have a little hammer that I can set a certain variable in the environment to a certain value, then I can know how does it affect my other variables in the environment. And in the case of a laptop and a laptop bag, I can say, well, if suddenly I can raise the purchase quantity of laptops. I ask a lot of people to buy laptops. Would it affect people buying laptop bags? And vice versa. If I ask a lot of people to buy laptop bags, would it affect people who are buying laptops? And what does it actually? What does this actually entail in machine learning in terms of generalization? So we talked about what are causal models, and we said, this is important for generalization. This is actually very important for many things. So for example, if you have a reinforcement learning task, so if you have an agent that's playing in an environment that's playing in multiple environments. So for example, the little grid world that we're seeing on the left. So each one of these rooms can be a little small environment. Any humans who look at it could say, well, the rooms have some similarities, but they're not exactly the same. So some rooms have keys, some rooms have blocks, some rooms have both keys and blocks, and some rooms have, just one of these, and some rooms have just blocks. And yeah, so basically any human who's seen, let's say, any two of these rooms should be able to generalize, should be able to learn to play in all of these other rooms. So we want our machine learning models to do something similar. So we want our machine learning models to be able to generalize to compositional and a diverse sort of compositional environments. So in order to do that, one of the best ways we can do this is to learn a causal model. So why would a causal model allow us to generalize? A causal model is basically the simplest possible representation of your data distribution, and they're also robust. So that means if I have a change of environment like the ones we've seen earlier, a causal model can represent those changes with the most sparse set of changes in my graph, in my model. So basically, it's saying if I had a causal model that I can just change going from one environment to another environment, I can just change a tiny thing in my model, and then I should be able to change from one environment to another. And this means that the changes are localized, the changes are sparse. That means that my models can adapt faster, and my models are probably more robust and transferable. So this kind of leads us to talk about invariances. So invariances and causality are not necessarily the same thing. So causal models implies that if you have a causal model, that implies that your model is invariant. But if you have an invariant model, it doesn't necessarily imply that you have a causal model. So under certain conditions, and also under certain conditions, we've basically found. So this is some of our recent work as well with Joshua and also our co-authors, and we recently found. So basically, if you are invariant, this is a known thing that if you want to be invariant to interventions, then you'll find a causal model. But you can also use a neural network that learns this invariance, that actually learns a really good causal model, because neural networks can model nonlinear relationships really well, and they can learn. They have really good. They have really powerful representation learning power. So we talked about most of the recent work, and I'll now move on to talk about what are the underlying challenges in applying causal learning to deep learning. So as Kara has talked about, in traditional causal learning, most of the time you assume that the variables are given. So if you have medical data, if you have biology data, if you're trying to model things like protein structures, and if you have medical data and you want to know the person smoking, does it cause lung cancer, all of the important variables are given. Variables like smoking and lung cancer, they're all given. But this is not necessarily true, and we can't take that for granted for many models that we use for deep learning. For example, if you have a robot acting in the real world, I can't possibly label every single variable, interesting variable that the robot will see. So the robot will have to go into the real world and will have to basically learn what are the interesting variables by itself. And this is not trivial. So this requires kind of your model to learn. There are two major challenges. So it requires your model to be able to extract what are the interesting variables, and then learn a causal model that models the relationships of those variables on top of it. So here's a really simple example of a physics environment where you have like heavy and light objects. Darker objects are heavier, lighter objects are lighter. That heavier objects can push lighter objects, but not the other way around. So if you look at even this very, very extremely simple environment, your causal, essentially what your model has to do is your model has to extract meaningful objects from it. So these are those like little triangles and circles from it. And then to be able to learn this causal relationship, which is demonstrated by this like a little acyclic tournament there, that heavier objects can push lighter objects and not the other way around. But actually learning this, learning this is actually affected by many factors in the real world. And we summarize them to mostly like 3 factors. So one is your physical nature of the environment. So the physics of the environment, whether or not objects move together, gravity, friction, and all of this. And this is pretty natural and people can think about it. So things that defines object and events. And other things like what the agent can see and control. So for example, if you have a colorblind agent going to the real world, even if the agent, even if color is an important variable in your causal graph, but if your agent can't observe color, there's no way the agent could model that. So then this affects you learning a causal graph. And it also matters what the task is. So things like, if I know how to drive a car, I don't necessarily know how to fix a car, but the mechanic would know very well the causal underlying causal mechanisms of mechanics of a car and should be able to fix a car. So what kind of causal models I learn roughly depends on those 3 different categories, 3 different categories of things. And I think this is something that people have started to look at, and it's a really interesting research direction for the future. And thanks. I think that mostly wraps up my talk. And thanks.
Thank you very much, Rosemary. That was great. I'm going to ask Carla to join us back on screen again. And so I need to get this out of the way so that we can get on to more interesting questions. You both agreed in your talks that correlation does not equal causation. And yet I know that there is some controversy, there's some disagreement between the 2 communities, statistical and machine learning, about causality and machine learning. Can you describe what that is?
Right. So I guess in a perhaps gross oversimplification, I wonder how Rosemary is, for example, able to learn the causal structure from the data without somehow equating this correlation to causation, right? So in my world, mostly, if I observe a correlation, I have to bring external knowledge to be able to sort of say, okay, so either the laptop cost me to buy a bag as opposed to the bag cost me to buy a laptop. So without this external knowledge, I wonder how would Rosemary's deep learning methods learn what was the arrow direction, right? So
you fundamentally are uncertain whether you can learn causal structure from data.
Just from the data. So either I bring data from elsewhere or I bring knowledge from elsewhere. But
I think Rosemary can answer this.
Thanks. That's a good question. So yeah, so that's a good question. So I guess like there are 2 things with it. There's the part of you are given the right variables or you're not given the right variables. And if you are given the right variables, so I think there's also a difference in thinking from, I think, like most of the statistical causal learning point of view and like the deep learning point of view. So I think in causal learning, from like the more classic causal learning point of view, a lot of causal learning was to help with scientists to answer questions. So for example, like to understand medical data and things like that. So their interventions are expensive. So you don't want to, and also you can't just perform any random interventions on any random person. Whereas in deep learning, a lot of the applications applications in things like robots and agents acting in the real, acting in like a simulated environment, or a robot acting in the real world. But there's actually less price that the agent has to pay for doing an intervention. So let's assume if the agent knows what the important variables are, and if they want to find out which direction, like for example, if it's a laptop that's causing you to buy the bag and or vice versa, you can actually intervene. You can ask the agent to intervene in the environment, and then you'll be able to see what the results are. And in the cases of where the variables are unknown, so it's true that this is a very difficult problem. I think so there's been basically thoughts. So there's been like some recent work in wanting to work in this direction. It's not an easy direction. So you have to, so I agree this is not easy because learning the encoder, learning the variables and learning the graph on top of it, they kind of go hand in hand with each other, and they're not independent. But you can use, like, for example, humans have very strong priors. And I think Josh Tenenbaum talks about it in like some of his papers, like the theory of causality and things like that. So you can use like human priors, like this, humans want a simpler model to explain the world. So he has this like famous experiment where if you turn on like different switches to the light and you ask them, does one of the switches turn on the light, but you haven't actually observed that switch, but you will mostly answer no because the other switch turns on the light, just because humans have certain type of like priors to say that. So a way of utilizing those type of priors in a model could help the model to learn a causal model. Of course, I guess there's no guarantee that the model can learn the right variable and the right causal model at the same time. But we don't have a lot of choice if we can't possibly label everything for our robots. So these are kind of like surrogate laws and surrogate targets that can allow the model to learn it to some extent.
Does there need to be a guarantee? I mean, both of you talked about the reason that you're working on causality is for its importance for model robustness and generalizability. If Rosemary's models generalize well, isn't that empirical evidence enough?
I suppose, yeah, I would say probably yes. But for example, this model that was sort of training one hospital data to sort of then use it in another hospital for deciding who to admit to the ICU. And unless you look deeply as to why, so the reason why they discovered this problem was because the prediction that asthmatics would survive better was a bit counterintuitive. So they used external knowledge to think, oh, hang on a minute, something went wrong with this model. And I think if we hadn't had that, hang on a minute, this goes wrong, maybe they would have just said, okay, so don't admit any asthmatics to the ICU, and perhaps there would have been a high cost. So I understand when Rosemary says, well, for my robot, it's not so dangerous. It can make a few mistakes. Whereas, for the humans, we shouldn't be able to live with those mistakes, right? We want to make sure that our models are very robust before we deploy them. So this is why, in a way, maybe we should be less ambitious, but more careful. Wherever causal predictions we're going to do, we should understand why we're making them, right? When we're going to use them for life, so to speak, life and death decisions, right?
Yeah, I agree with, I actually agree with that. So I think it really depends on what the risks are. And even for like deep learning models, I fully agree that we should take on any prior knowledge that we already have. We actually tried this for our paper to take on, like, let's say if you are given like a partial graph that you know what part lay the graph is, and you have to learn the other parts of the graph. The model actually learns way faster and everything. So
in a sense, we're not learning from data alone. There's causal structure in some sense included in the model as priors or structure.
Yeah.
So that partly answers the question as well, doesn't it?
Yeah. So maybe we just maybe the traditional sort of statistical causal inference would go by stages, right? And maybe we learn the structure from past data, and once we feel that we know quite robust, because we've conducted lots of different studies and they seem to suggest that the arrow goes in this direction, then we take it as a strong prior that my causal diagram is this way, right? Whereas I think Rosemary has this luxury of being able to run many worlds in one go, right? And learn what are the robust structures of causality in applied topics like physics or medicine. We only have the real world, so we have to run lots of experiments sequentially to sort of learn this, right? So mainly saying the same thing, and it's just a matter of how we aggregate the evidence.
Yeah, exactly. And also, sorry, I'll just add one point also that I think evaluation for a deep learning model is not necessarily so trivial either. So a lot of deep learning models, so not a lot, but some of the deep learning models that models causality don't necessarily learn a structured graph. So they will have like an unstructured representation that basically can predict interventional outcomes. In this case, it's actually hard to evaluate the model because in order to evaluate it, you have to evaluate it on all possible interventions. And for like an agent playing a game, for example, you have to set the agent in all possible state that can be in the game. And and basically evaluate all possible actions. So that's just very expensive. So that's actually a good open question about like how to evaluate these type of models.
When I opened this session, I talked about the hard open problems I was quoting in AI and machine learning being to do with causality. Aside from generalization and robustness, are there other benefits to incorporating causality into machine learning, and I guess vice versa as well?
Yeah, so I think there is. So I don't know whether you consider sort of like fairness and biases in the data part of generalization. So certain school of thought would say that. So there's been a lot of debate, for example, of equality of opportunities now with, say, Black Lives Matter, and we know that a lot of our training data is perhaps too based on the the experiences of maybe the non-ethnic minorities. And one worry is that perhaps what we're learning is kind of like biasing against the ethnic minorities, right? So if we were to be able to learn or sort of impose this causal structure, we can try to redress these problems and perhaps sort of like break that arrow of selection bias, if you see what I mean. We know that our data has that bias, and we can sort of like redress it using causal tools. So I think it is important to be aware of the way the data was selected and how we can avoid these biases in other settings.
Yeah, and I agree. And also, like, I think for example, like really simple things like recommendations, like the example of like buying the laptop or the bag. So I think things like that is important to understand what is causing what. In some
it helps with interpretability.
Yes, and with some reinforcement learning as well, and yeah.
And Carla, I am quoting from one of your papers here. We believe paradoxically that machine learning methods that are often criticized for their black box nature may increase the transparency of applied research. Would you care to expand on that?
Yes, so in statistics, again, sort of traditionally, you would be asked to define your analysis plan from the beginning before you see your data. And then it's kind of set in stone to prevent you from sort of cherry picking and sort of like, digging around for results. But paradoxically, it kind of, you then at the same time try to get the best fitting model. So there is a lot of, I'm going to add quadratic terms and I'm going to add interactions, because the model that you set at the beginning is probably not the best fitting model. And I think you end up sort of digging around. Whereas if we were to specify an algorithm that is sufficiently data adaptive, I think it can be pre-specified and flexible at the same time. So I'm trying to sort of like break a little bit the barriers to adoption of more modern methods. Many of my colleagues would think it's like searching around for results, but I think if you do it properly, it doesn't have to be that way. It's about finding better solutions. Huh?
Yeah. Thank you. I have one more question to ask, and it's about what is the next research question that you are trying to answer?
Ooh. So,
Rosemary, are you ready to go?
Sure. I think mostly like what I talked about at the end of my talk. We have we're actively working on that. So basically, how to learn what are the essential so we are identifying what are the essential ingredients for applying causality in deep learning, and what affects learning those basically variables and the causal models at the same time. So that's one thing we're looking at. Also, like I think releasing data sets that in environments that allows you to work on that. That's also really important, because a lot of the data it's basically it was like pre-deep learning data. So you know there's like 1,000 examples, and you can't really train a deep learning model on that. So yeah, so these are kind of like important questions. Well, these are kind of the questions that we're looking at next.
Thank you. Carla?
So I'm interested in looking at sort of what we call dynamic treatment regimes, and sort of like in time. So what are the sequences of treatments that that we should give at different time points of the patient's journey through health, and what is the optimal time to add the treatment so that you maximize this benefit, right? And personalize it as much as possible to your own past. So, because I think there is a lot of data out there, and if we get this structure right with the causal structure right, I think we can do much better than we currently do.
Perfect. Thank you so much, both of you. This has been an absolutely fascinating discussion for me, and I've learned a lot. I hope that the audience has too. I should mention that there is the opportunity to join the Q&A session in about 10 minutes time. I hope many of you will do so. And I'd like to thank Rosemary and Carla for their brilliant presentations and participation in this discussion. Thank you.
Thank you.
Thank you very much, ladies. That was an absolutely brilliant discussion. Again, so much depth on this stage. One of the things that I've just been enjoying so much watching the cutting edge stage is how deep we're getting into some of these topics. And of course, it being the cutting edge stage, you would expect that, but it's wonderful to see it happen in real time here at CogX. So thank you for that. As Libby said, please do go join the Q&A. It's going to be starting on the hour, go for about half an hour, depending on how many questions you guys have already submitted. Of course, if you haven't already submitted your questions and you would like to go join that session, submit more, or even just go and watch and see what everyone else is asking. You're very, very welcome. Next on this stage, in the cutting edge stage, is a talk on scaling voice technology. That's going to be starting here at 5 o'clock London time. Depending where you are in the world, it might be a slightly different time, but please do come and join us for that. That looks to be another brilliant session here on Cutting Edge. And of course, in the meantime, if you're not going to the Q&A, go and check out some of the other talks. The expo's there for everyone to go and see what's being exhibited, and of course the networking rooms too, so that you can hopefully meet some fellow attendees of CogX. Until 5 o'clock, please enjoy yourself, and I'll see you then. Thanks very much. Hello everyone, welcome back to the Cutting Edge stage and to our penultimate session in this track and indeed of the conference itself. We're going to be talking about scaling voice technology, and with that I'm just going to go straight into introducing our moderator for this discussion, Catherine Breslin, Solutions Architect at Goldstaub. Please join me in welcoming her to the virtual stage.
Thanks a lot, Gemma, for the introduction. And it's really great to be back here on the cutting edge stage at CogX. I'm really excited to be here again. And I'm thrilled that we've got three amazing guests today who have keynote talks talking about their real world experiences in scaling and building voice and language technology for the real world. So to start us off, we have Dr. Heidi Christensen from Sheffield University. She's a senior lecturer in computer science. We're followed by Andy Webb, who's head of voice and AI at the BBC. And we're finishing up with Helen Lyashenko, who is Software Development Manager at Amazon Alexa. So without further ado, I'd like to introduce Dr. Helen Christensen, Heidi Christensen.
Hello, everyone. Thank you very much for inviting me. It's really exciting to be on this stage. I realize I'm the academic input to this session. So my slides here today is I'm going to talk about scaling voice technology, the healthcare domain case, if you like. Let me just... So first I wanted to talk a little bit about what state of the art looks like in voice technology, although I reckon you will hear a lot more about that later on in this session. So obviously we're now quite used to having a lot of usable and very used voice technology everywhere. So there are apps we can talk to, they will understand us sort of, they will generally assist us when we're communicating. We could have live captioning and video calls like this one. We could get away with speaking to robots, etc. So mainstream speech tech has matured a lot in the last decade. There's lots of successful applications and they're really pushing boundaries of conversational interfaces. So we're really here to talk about scaling voice technology and how we get the next 10 years right, if you like. So I'm going to question a little bit what sort of scaling we are talking about in this talk here. There are a lot of options of factors we could scale. So when you're training, for example, speech recognition, certainly looking at the number of hours you might have in a speech corpus is something you might do to kind of scale things up a lot. So Amazon recently kind of talked about how they're now training acoustic models with millions of hours of speech. That's definitely scaling things. Or you might think about how you could scale the number of voice-enabled personal assistants, for example, that are sold. Again, huge amount are already out there. I'm going to cut to the chase in this talk here and give you the talk's conclusion straight away, which is that I think we also need to talk a little bit about scaling downwards, if you like. So with this, I want to talk a little bit about how it's really important when we scale upwards, we also start looking at the details and getting the details right in healthcare domain when we're talking about that case, if you like. So this is about getting personalized solutions, solutions with detailed information from clinicians, etc. So all of the cutting edge or current cutting edge is for typical voices. So it's typically kind of targeted at generally healthy and well people, not for the too young, not for the too old. But I'm really interested in the sort of cutting edge corners, if you like. So what can we do for people who are not typical, not well? Perhaps they might not know that they're not well, but what can we do to kind of help them with technology? So to sort of put this in perspective, if you like, my research interests are particularly on pathological speech. How can we detect pathologies? How can we treat them? And in general, how can we break down some of the barriers for this group of people when they are accessing, for example, personal voice-enabled assistants? So this is really an equality and inclusivity issue, as well as being an interesting research topic. So why is this important? Well, we could look at some of the conditions that I work with, people who have these things. And for each of these conditions, people are affected in different ways through different lifespans. So something like cerebral palsy occurs at birth when something goes wrong. At the moment, it's about 1 in 400 births in the UK, and you are affected for life. So you will have often severe mobility problems, and it also affects the way you speak. Another big group of people I work with is people with dementia. So this affects about 850,000 people currently in the UK. And it's also now the most common cause of death in England and Wales. The risk increases with age, and it's a slow onset. So you might not know for quite a long time that you have early signs of dementia. Then there's something like stroke. People estimate there's about 100,000 cases a year. These are often relatively young people who are living active lives. And so this is a huge life-changing event. And we really need to help them to get back into living active lives again. And then there's something like mental health. It's estimated that around 1 in 4 people in the world will be affected at some point in their lives. This is a condition that may come and go. You might feel well for some years and then less well for some time. So how can we get technology who can bring different life quality improvements in these cases? So some of these things are slow onset, some are for all of your lives, some are for the end of your lives. How can we kind of make things better with technology? So in this talk, given we just have 15 minutes, I'm going to dip into 3 research case stories, if you like, from my team, what we're working on. First of all, disordered or dysarthric speech recognition. Secondly, a little bit about how we might analyze conversations, what sort of things we can do in that field, if you like. And finally, pathology detection, such as dementia. And I'm going to talk a little bit about what we've achieved, what's left to do, and what the kind of main challenges are, if you like. So dysarthric speech recognition. The motivation here is that people with atypical speech, this is often caused by long-term conditions like cerebral palsy, or it could be a sudden traumatic brain injury, stroke, etc. For these people, it's suddenly really difficult to communicate effectively, both with humans, but also with machines. And on top of that, they often have mobility problems, so they can't really very easily use the keyboard. So they could really do with having speech recognition available to them in a way that it's now available to most other people. But of course, they can't use mainstream speech technology. Is just not tuned to their type of voice. So the sort of applications you can imagine if you solve this research problem would be dictation systems. It would be so much easier for them if they could speak as an input to text generation. Speech recognition for controlling smart home devices, so something like the Alexa system, for example, or speech recognition for communication aids. So you have a voice input, voice output technology would also be really useful. So I just want to show you a little bit about the path of mainstream ASR starting back in 1970. And how you went from kind of single word command and control systems to voice-enabled personal assistants, and now we have much more interaction systems. In the world of dysarthric ASR, we're basically still up in the very beginning. We are only just moving away from the kind of isolated word case. So what are some of the things we can do to make systems that work for this group? We definitely know that we need to personalize systems, so we need to think about what sort of words are we designing them for. We can't have them say any words or any phrase. It's often necessary to cut down to really limited amounts of words. We also know that we need to tune the models to the specifics of a person's voice. Another thing is that we have to find out in the sort of research space how we make use of very little data. So it's definitely not possible to record millions of hours like Amazon can do. In fact, some of the databases we have as little as 20 minutes per person. So we really need to work out how we can make use of this, how we can leverage typical speech databases, explore alternative representations, use conversion techniques, etc. Common for all of these things is that they do work. However, we are still far off mainstream performance. So we're far off being able to give a phrase-based dysarthric speech recognition system to someone. The other main thing I kind of work on is analyzing conversations. And this goes from anything like analyzing, finding out emotions when people talk to each other, their goals, etc. One of the big aspects of this is communication aids, where people such as the lady here that I've worked with for probably 10 years, she's using a communication aid to try and help her speak to people who don't know her well. People know her well, they understand her, but most people don't. But they're really hard work. They're not really conducive to having a natural interactive conversation. So the solutions are, there's lots of different things we can do. We can have better input methods. If we could recognize her speech, that would be much better. We also look at how we could recognize a full message, not just what she's saying, but how she's saying it. And we can make use of context, who she's speaking to, is she at the GP, isn't she in a shop, etc. All of these things you can kind of add in. Another aspect of conversation analysis we're looking at is to try and unpick what happens, for example, when a psychotherapist is speaking to a client, and try to understand the dynamics of a conversation. We know that if people can stay with the sessions and come back for all of the sessions, there's a much bigger chance of having a good recovery. So we're trying to see if we can automatically try and detect when things go wrong. So we're looking at things like depression, anxiety, synchrony, is there empathy expressed, etc. So we kind of know that speech analytics like this can reliably track all of this in the lab, if you like, in research experiments. How we really need to learn how to combine all of this for real impact. So how do we make a system out of this that is actually useful for people? And how do we find out what users really want from such systems? And then finally, there's a lot of work going on at the moment to try and see how we can kind of automatically detect signs of pathology in a person's speech and language. So the motivation here is that people with cognitive impairment, for example, as a result of Alzheimer's disease, they often show really early signs of a condition in their speech and language. So this could be up to a couple of decades before the doctors were kind of detected. If we could detect these automatically, we could really improve treatment, we could save time as well as money. And you could imagine you could screen the full population for things like Parkinson's disease. You might stratify people with memory problems. You might go into looking at long-term tracking of people with mild cognitive impairment. So there's lots of applications, if you like, of this, if you could get the basics right. And we know from research that people have looked at, for example, Iris Murdoch's books. So going back 10, 20 years from when she was eventually diagnosed with Alzheimer's, you can see that her books are less complex. And the same with Ronald Reagan's speeches. So he was famously diagnosed with Alzheimer's about 5 years, I think, after he left office, but you could actually see it in his speech much earlier than that. So what have we tried to do? So we try to look at the sort of conversation that a doctor has with their patients as they come into clinic, and try to find out whether we can automatically capture some of this. We really need to have an easy to use and quick and reliable test for people to take at home, because it's very stressful to come into clinics, it's very costly as well. So we've tried to see how far we can kind of get with automatic methods in this area. And we've looked at various automatic methods, including replacing the doctor with a virtual agent. So currently this system is the one you see on the right here, CognosSpeak. It will ask a couple of questions of you, ask you to do a few tests, and then kind of work out whether you are at risk of developing dementia and should come into clinic. And these are the sort of questions that we look at. So things like, well, if you come in today, what are you hoping to find out? Long-term and short-term memory questions. So we're really hoping to be able to track people's cognitive health over time. We have a lot of recordings at the moment. And of course, with current sort of data-hungry algorithms, we need a lot more data. But we are able to show good accuracy, which is good. They're already equivalent to existing standard tests. People like talking to the head, which is good. They find it more friendly. It's less kind of stressful than some of the other tests. And it doesn't take too much time, so it takes about 11 minutes on average. However, we still need more data, and we need to explore lots of things. For example, things around language and accent diagnostic tests. And we need to test a system like this in GP clinics, for example. So this was a quick run through sort of 3 research cases, if you like. There are still many challenges. There's a lot we can already do. And there's some key themes you've probably picked up on. So clearly for all of these areas, it requires a big interdisciplinary team behind the scenes. So I regularly speak to neurologists, psychologists, linguists, etc. This is definitely not just something you can do as a computer scientist sitting in your own lab. All of these solutions need personalization. So this is going back to the scaling up by scaling down into the details, if you like. all of these areas in the healthcare domain suffer from having access to too little data, really, for porting the methods we know work well in the kind of mainstream domain into this area. And we really all need to kind of be aware of how we show real impacts when we move out of the lab. So this is where I feel like university academics really need to work with industry to make that leap out of the lab. So in summary, we have very promising research results. However, we really need to work well with industry and universities to collaborate to put this technology in the hands of end users and clinicians. And I feel universities have a big role here because they have access to this very interdisciplinary team. So to go back to one of my very first slides where I gave away the conclusion. So as you saw, in this area for working for these people, we really need these personalized solutions and solutions with detailed information from clinicians. So all of these systems, we've worked closely with clinicians to learn about what happens, what are they looking for. And in terms of the next 10 years, I really hope we can show impact from this cutting edge corner, if you like, technology. So thank you very much. And I think I will pass over to Andy now, who is at the BBC.
Hello, everybody. Welcome. Thank you very much for that, Heidi. It's really interesting to hear. I'm going to be talking to you about scaling voice experience through a slightly different lens, through that sort of business and sort of strategy lens. When we think about scaling, we obviously start to first think about starting off very small, like what are your beginnings? And how do you start to grow your involvement within voice? And how does voice start to play a more important role within your organization? So I'm going to take you through essentially what was the BBC's journey. I started in voice about 3 years ago, so I'm a bit of an old hat almost in it now. And obviously we are a huge publisher onto platforms such as Alexa and Google. And not only that, last week we launched our own assistant as well. So I'll take you through the journey through that and thinking about how we had to sort of scale to be able to work in that kind of evolution. We think about the first question. I'm just going to start to share my screen. If we think about why voice is important, it's almost after sort of 30 years of kind of graphical user interface digital experiences that we've had, they've all started to sort of plateau in terms of that user experience a little bit. If you think about some of the differences that exist, lots of the websites are still sort of quite sameish. They've got categories kind of like product pages, about us, contact us, checkouts. Mobile apps have got the quite sameish now a bit as well. There's scroll up, scroll down, swipe left, swipe right. It's news feeds that sort of dominate it. And if you think about TV applications as well, they've started to come a little bit sameish as well. There's genres, there's categories, there's A to Z essentially. We've sort of reached the limit of just how good we can make these branch tree user journeys to be able to get people where they want to be. Now, we've done a really, really good job of that, but I don't think anybody would kind of disagree that we're now up against this law of diminishing returns that really sits in there. So kind of enter voice and natural language. So we believe voice will evolve to become this benchmark for great user experience. Not necessarily by itself. Voice will deal with that kind of audience shift that now exists into ambient computing. You know, we're living in smart homes, we're driving smart cars, we've got smart headphones, smart watches, and we're surrounding ourselves by that kind of computing power. But it also has the potential to sort of truly revolutionize the user experience of our already existing large-scale digital products, as that voice user interface and that graphical user interface start to build tighter interdependencies between each other. And we'll really start to, again, see diversification start to come through in digital experience, and this whole new wave of innovation as we sort of explore great user journeys. Now, that cut through of navigation that voice facilitates will really transform our audience experiences, but it will also have effects on how brands are reflected themselves online. If you think about it, we spent 20, 30 years building these incredible brand experiences, really rich, surrounded by content. And suddenly you can just turn up and say, oi, play Radio 1. And you can just cut straight to that piece. So there's pros and cons about voice, and essentially it's always this balancing act now between sort of discoverability and ease of use, and that the ability for us to represent our brand effectively online. So for us, our sort of starting point was really to go back to the BBC's original mission. Our creative and editorial question is always how to inform, educate, and entertain in a conversational medium. Inform, education, and entertain is the BBC's mission. And that creates then the business and technology question, which is how do we create a sort of a scaling strategy that enables that conversation for us to take place. So we started off with this sort of 4-point strategy that we presented into the business, and all the best strategies keep things very, very simple. And for us, we wanted to start off with a more modest investment around here and start to think about things. So for us, it was to start to invest in conversational design. And if you think about conversational design, we're very good now at talking to users when they have a screen. Take away that screen and we have very little experience of talking to them, or indeed when they can talk back to us. So that gets you thinking again about the differences that exist between a graphic user interface and a voice user interface. And one of the first things you come up to, and that starts to challenge you, is you realize that the internal naming conventions you've been using within your business for a long time actually become quite difficult for a natural language processing engine to be able to sort of get through. If you quickly go to the BBC Sounds website, you'll see on there we've got Radio 1, we've got Radio 1 and Radio 1 Extra, we've got Radio 1 Anthems, we've got Radio 1 R&B Anthems, we've got Radio 1 Dance, we've got Radio 1 Breakfast Show, we've got Radio 1 Breakfast Show Best Bits. So it's easy to really see how natural language processing engines can start to sort of run into problems when you've got that repeated use of words that's used to describe sort of differing assets that exist within your business. So actually one of the simplest tricks that helps you be able to scale and helps you get all of your content onto there is not necessarily to work with the tech and refining the tech a lot to be able to sort of distinguish between various pieces, but actually to think about it from an editorial perspective and just to change your naming conventions around the content and to have that foresight that as we develop new programs, that the names should make them searchable within a digital experience and within a voice-first experience. We set this kind of criteria as we wanted to get up to the second level that really sort of justified spending additional money and sort of scaling even more within voice. Because one of the biggest mistakes people make is sort of overscaling their products at the beginning when demand is low. But these numbers kind of really gave us a lot of confidence to be able to move on. So we launched our first music skill on Alexa, and we have a fantastic relationship with Amazon who sort of helped us go through and helped us work through all that kind of editorial naming conventions to make our assets available. And to date, we've played over 1 billion pieces of content, 100 million news briefings, we have 2 million weekly users who exist across our voice assistant real estate, and at the moment we've really just kept it focused on the UK. Globally, the BBC has probably about 450 million people a week who kind of consume a piece of BBC content. So actually our largest audiences actually exist outside of the UK, which we haven't even approached yet. So you can clearly see the potential that exists for doing what we do already now and not having to sort of overinvest, and the ability for us to scale that hugely to new audiences. The next stage that we kind of went to as we start to move this was to think about how do we start to deliver these new experiences that wow the world? And what that really means is how do we evolve products that start to maximize the use of the format that is available? We learned very much from when we took content from print and tried to put it on the web that it didn't really quite translate in that way. And likewise is the same of when you take a program that was designed for, say, radio, and then try and put it into an interactive voice environment, it doesn't necessarily sort of work as well. It's good if you're using a smart speaker or something just to replace your DAB radio or something like that. But if you actually are thinking of it as a piece of content and you really want to maximize the benefits out of it, you have to start to design for that new format. So for us, one of the things we needed to do was to think about, to do that at scale, we need to start investing in tooling. because tooling is actually what takes content production out of the hands of software developers that are very expensive and starts to put that back into the hands of content producers and those creative people who develop our programming and develop our services, who audiences have built up that long relationship with for us as well. So this tooling, I guess when you go back a few years ago, was this sort of thing that you had to approach with a lot of caution. First of all, really just because of the market that was existing around it. The market was very, very nascent at the time. I don't think there are any tooling companies in existence that were in existence about 3 years ago that haven't been acquired or haven't changed hand. And of course, that's meant consequences for people who built their experiences on that tooling. So for us, as well as that, there was this kind of regulatory environment within which the BBC sits. You know, we are a news organisation. There are various rules in various domains around the world about where we store our content and have that available. So for us, it made sense to start investing in our own tooling. So we started to create this tool that basically just allows editorial staff to be able to drag and drop and to be able to sort of create workflows and processes to be able to sort of publish their content out. And there's a number of really good tools that are available out there on the market. But for us, we still have our use case that sort of determines that we need our own. Now, this let us start to work in a number of experiences. And the first use of that tooling, the first thing where we allowed editorial teams to suddenly create experiences themselves without the software engineers playing such a huge part in it, was around the Alexa launch for children's skills. And we were one of the initial launch partners for that. And today we still maintain this kind of 5 interactive brand games that were made completely by our editorial teams. We have sort of 25 children's stories that exist on there, and a number of sort of music and song anthems that go through. And one of the other things that enabled us to do was to bring our audiences closer to our broadcast domain. So most of the editorial staff who work in our team essentially come from strong audio backgrounds. They come from program making for radio. So there was a great opportunity to start to bring audiences much closer to our traditional radio output. And radio within the UK is still the single largest form of content, new content discovery that exists anywhere. So it really made a lot of sense to be able to bring those two together. So we did this great trial that was, again, produced on our tooling by our editorial teams who worked with the Radio 1 Breakfast Show to be able to bring a live experience where Greg was playing with his guests in the studio, and audience people could also play alongside online as well. Through their Alexa voice assistant. And it met with this sort of really terrific response. It really cut through with sort of young audiences as well. So we started to show, again, that, you know, once we developed the tooling, we can start to scale our involvement in voice a little bit more and a little bit more. Now, you do start to run into some problems at this stage. And that's because when you start to build deep, rich experiences, naturally, what you really want to do is start to publish them to multiple platforms. But all platforms have rules. All platforms have sort of things like reserved naming conventions that exist on them. And the problem is, all of these rules are not the same. So often you have to build a slightly different version of your experience to work on another platform. And that's okay at small scale. It's not terribly efficient in resources or in the kind of marketing spend you'd have to do. And if you want to achieve absolute consistency in experience, you have to design for that from the beginning. And often that means you can't then exploit the full benefits of each platform because you've designed for the lowest commonality that exists across all of those platforms. So, and then you have to think again, what happens when more and more platforms start to become available onto the market? You can't scale engineering teams that have bespoke knowledge within just one platform and then another team that has bespoke knowledge within another platform. So that led us on to the sort of the third stage of our sort of our 4-step strategy. And in order for us to sort of take that, the reality is you have to say we had to take a bit of a leap of faith. There were a number of things that we had to believe would come true to be able to do this. We had to believe that voice was a long-term investment that was going to be paid back through better user experience and improved distribution. We had to believe that there will be many voice assistants in the market, and that this is essentially a future trend, and that the only way we could scale in a reasonable, fair, and non-discriminatory way would be to seek a new method of distribution. We had to believe in coexistence, and the future will not just be one person talking to one assistant on one device. Consumers will still seek out the brands that they kind of trust and love. You have to believe in complex use cases as well that will require greater brand control and depth of conversational design. You need to believe in that depth as well as the breadth to go beyond simple distribution. And so this story broke last year, our own conversational assistant that allows us to address those scaling challenges. It allows us to deliver consistency and experience for complex interactions. I should say we still firmly see a world where we support the breadth use cases through distribution on platforms such as Alexa. And we have some kind of interesting plans in the pipeline for that. However, this also develops the necessary technology and APIs that allow us to democratize the natural language interaction across our existing digital real estate, which is what I discussed at the beginning, those interdependencies that will start to build between the sort of voice user interface and the graphical user interface. Simple example would be incorporating natural language search or hands-free use cases of mobile applications. So we launched a scaled-down version of Beeb last week, and really it's about testing lots of the sort of the plumbing that we've got going in, and making sure we're able to bring forward much richer use cases throughout the rest of the year. So scaling beyond publishing, so one of the lessons we've learned is tough. Building conversational UI is tough. If you look at all of the companies that sort of lead the market in this space and the resources they have allocated to it, you have to kind of believe in this one other thing if you're going to put your foot into that, and that is one of partnership. There are incredible high barriers to entry, although the technology is starting to become commoditized relatively quickly afterwards. And successfully scaling that means that we have to think of our digital services. Our future digital services will now be developed in partnership with technology providers, either big or small, who have kind of expertise in kind of the components that you want to plug into the pipeline of technology. And what becomes important for us is to maintain that actual pipeline and not the component parts themselves. So owning the pipeline is really what allows us then for each given context to assemble the right amount of component parts. Those that are kind of being provided by external providers, such as speech recognition, natural language understanding, natural language processing, language models. All of those can be provided by other people. It's not necessary or relevant for us to develop a core competency in them if we think they're going to start to become commoditized in sort of relatively short period. There are some use cases where we see open source, things like open source language models still being quite useful to us, or co-development of language models. And that's because, you know, the BBC, we generate content in 42 languages worldwide, and it's not necessarily all the common languages or the languages that would have a lot of commercial interest around them as well. So we do things like Hausa or Somalia and lots of underrepresented languages in terms of like the global economy. So for us, we just want to make sure that we don't become bogged down in the technology, which is very, very easy to do, but more just to become concerned with the application and the assembly of what drives scale. So coming on to the fourth sort of point that exists there, there's one thing that will probably really drive scale ultimately, and that's interoperability. So we can kind of regard the coexistence that sort of Jeff talks about here and has been on stage talking about, and you know, we've seen the demos between Alexa and Cortana interoperating between each other. But we have to kind of view coexistence still as really a first step towards full interoperability, and that is the piece that will sort of drive real scale in where we go. So coexistence is practical problems. So technically that's reflected in how many kind of wake words can be supported and the diversity of the frameworks and the performance of the edge processing equipment to recognize those wake words and to be able to route a user's utterance accordingly. Also,
I'm going to jump in quickly and just interrupt you there for a second. And I think this would be great to continue in the Q&A session afterwards. I'm just conscious that we're running towards the end of the session now, so I don't know if you have a wrap-up slide.
Yeah, sure. Okay. There you go. How's that for a wrap-up slide? so really, we do see interoperability as kind of something that's going to go quite big. And if you think there's only two ways to make money in the world, as the old saying goes, bundling or unbundling. What that really means is that to achieve maximum scaling, we have to be prepared to play smaller parts in other people's conversations and let them play smaller parts in ours, essentially unbundling that full assistant experience. And that's going to require a focus on machine-to-machine conversation, bot-to-bot transactions, rather than just that kind of human-machine conversation that we have today. So it's not really kind of like as far out as it sounds, really, because it's really how the internet was built today. The internet is a connection of networks. Typically, you are served by your local network, and only when you need to go out for pieces of information do you actually go outside into the wider world and be able to sort of bring back that piece of information. So it's quite a similar concept to what we do. And we think ultimately those 4 steps is the kind of the trajectory of how we scale our experience and our involvement within voice. So I'm going to hand over to Helen now.
All right. Hello, everyone. Thank you very much for inviting me. I am thrilled to be here at CogX. My name is Helen, and I'm a software development manager working on Amazon's Alexa. I've been in the Alexa organization for about, well, almost 5 years now. And in that time, I've had the privilege of working on some really exciting technology. So what I'd like to do today is, I am sorry, but the device woke up. Alexa, stop. The power of, or the excitement of doing a live talk from home. Anyway, so what I'd like to do today is to share just a taste of some of what I've done over the past couple of years and hopefully inspire you to think about scaling voice technology in a different way. Think about a different dimension of scaling voice technology. So first, let's go back in time. When Alexa first launched, our devices looked a little bit like this. Not quite, I think this is a later generation, but what you're looking at is an Echo device, and you interact with it using your voice, and it responds with sound. The fact that this device enabled voice-driven interaction is what made it so novel, so futuristic, and that's what really attracted me to the organization. But these days, our devices tend to look more and more like this. They're not just voice in, voice out, but there's a screen, there's a visual element. That's because screens are actually quite useful. They can enhance the voice interaction by displaying additional engaging educational content. And they're useful because, well, sometimes the best response is visual. So if you ask, show me pictures of cats, which of course is a very critical use case, you need a screen to really deliver that experience. When I started at Alexa, I worked on question answering, which was very new to me at the time. It was, I really have to stop saying her name. I apologize, she keeps waking up. So yes, it was something that was really new to me, and I learned a lot. And then around the time that these devices with screens came out, I moved to multimedia. On a personal side, I love visual art, so moving into this visual space was something that was quite interesting to me. So I moved to the multimedia team, my team, and what we own is the systems responsible for enriching Alexa's question answering capabilities with visual content. Now, when I say question answering, I'm talking about interactions like how old is the Prime Minister of Canada, as opposed to some of the other things that Alexa is capable of doing, like playing music and controlling the lights in your home and so on. So my team is the one that delivered the kind of visual experiences that you hopefully see here if technology is working well. And for the purpose of this talk, I'm going to focus on images as opposed to other kinds of multimedia. So just a bit of background information. Question answering involves some natural language understanding. There's usually some knowledge graph that gets queried, and some other steps that are needed to generate the correct response. This happens first, and then our systems are asked to provide visual content for that response. And what we typically get as input is some semantic information, like a semantic entity, and then we use that to query our image corpus to identify what we think is the best content to display on the screen. So in the example here of who is Grace Hopper, the input would likely be a semantic entity representing Grace Hopper, and as output, we would return an image similar to what you see here. And in case you were wondering, Grace Hopper was a pioneering computer scientist and one of my heroes. When we started, our primary focus was on increasing coverage. And coverage is pretty easy to understand. It's a metric, and it's the percent of the time that Alexa's answers are accompanied by an image. Increasing coverage is fairly easy if you have a limited domain like music, for instance, but it's so much harder when you're looking at the entire question and answer space. Alexa is capable of answering questions about pretty much anything, which means that we need to have images of pretty much anything. That's a big challenge. So this is why we regularly assess our performance. We identify gaps and we take effort to fill those coverage gaps. And we fill gaps by identifying appropriate sources, licensing content, and ensuring that we can retrieve that content at the right time. So to support doing this at scale, we built an image ingestion pipeline. And some of the engineering challenge associated with this has to do with the differences between different sources and being flexible. In general, it's all about flexibility. So sources might have different access methods. For instance, one of them might give us a data dump, and another might have an API that we have to use to access data. Maybe there's a data stream, could be something else. There's also potentially differences in the semantic namespaces or annotations that they use, or maybe there's no semantic annotation at all. Maybe it's just an image and some text, or maybe it's just the bytes of the image. That's all we have to go on, in which case there's there's extra work required to extract meaningful information so that we can retrieve the right image at the right time. And also, depending on the source and the type of data being ingested, the pipeline has to be flexible enough to support arbitrary processing steps. So there could be different steps that we have to take at different times. So there's another element of flexibility. And these processing steps, they could be running different machine learning models or something else. So why do we need machine learning models? Well, I talked about coverage, and that's an easy metric to measure, to understand. a request comes in and either we're successful or we're not. And if we only focus on coverage, then we won't create the optimal experience. We're very customer obsessed at Amazon. So not only do we want to return an image, we want to return the highest quality, the most highly relevant image that we can. That's our goal. And one challenge we face is, how can we do that automatically? How can we tell that an image is relevant? How can we detect that an image is aesthetically pleasing or more aesthetically pleasing than another image? And if you think about it, how can we even measure improvement in quality? These are some tough problems that we have to solve. We continue to innovate in this space by applying the latest computer vision and other technology to deliver the best possible customer experience. And now I want to highlight some of these customer experiences, so I really hope that you're able to see my presentation. Otherwise, this really won't make much sense. All right, so these are all things that my team has delivered, and we're very proud of them. So the one that we're looking at right now, if you have an Echo device with a screen, then you've probably noticed news stories that tend to cycle through on the home screen. And when those first launched, the background behind those stories was the same as any other content. Nothing unique about it. We wanted to make that experience more engaging and more informative. So my team built the tools and did the integration that allowed those news stories to be illustrated with relevant, high-quality images like what you see here. So now each story has its own background and each image is related to the story, making the home screen that much more delightful. We focus on delighting customers with every interaction, no matter how small. When you used to ask questions about sunrise, sunset, or just the time in Tokyo, we used to give you a response with the answer on a blank screen. Now that answer is accompanied by beautiful images. If we have images of your hometown, we'll display it. If you ask for the time in a specific location, you'll see an image of that location. Question understanding, image ingestion, image querying, everything has to work together to make that possible. And okay, just one more. This one I'm really excited about. This was a lot of fun to work on. So recently, we started looking at events and trending content, something that requires really up-to-the-minute images to be impactful. We don't want to just return generic content. We want to wow our customers with something extra. And this is why when you ask about the Best Actress winner on Oscar night next year, not only will you hear who the winner is shortly after the winner is announced, but you're also going to see an image of that person accepting the award on stage on that night. I think that's pretty cool. So delivering this kind of up-to-the-minute, highly relevant, automatically detected and ingested content is an area that we're continuing to develop. And those are just some examples of the ways that we improve the customer experience every day. And there's always more new opportunities for us to improve and delight. So I hope this was interesting. Thank you.
Thank you very much to all three of our speakers there on the voice session. That was absolutely fascinating and so great to get three quite different perspectives from three different areas all around the same topic. And hopefully what's happened is everyone watching has had lots of shall we say, seeds being planted and hopefully lots of questions coming up with ready for the Q&A session, which actually is going to be starting in 10 minutes time. So go grab yourself a drink or go and run to the bathroom, or go and network or do some tweeting, whatever you'd like to do. And then come back in 10 minutes time for the Q&A, which is still going to be, all three speakers are going to be part of and moderated by Catherine. So until then, as I say, go and have a break. And then if you actually want to come back to the next session on the cutting edge stage, which is going to start at 6, if you're not coming to the Q&A, that's going to be on the future of computation, AI, ARM, and Risk-V. So you can come join that as well. 2 great choices, and I hope you will choose one of them from the cutting edge stage. Thank you very much. Hello, everyone. Welcome to the final session on the cutting edge stage today at CogX. I hope you guys have enjoyed the whole of the conference over the last 3 days and have seen some amazing talks, and hopefully been able to do a little bit of networking, albeit virtually, through some of the various different rooms and Q&A sessions and whatnot that we've had for you guys. It seems quite fitting that the final session of this stage, and indeed of the conference, is on the future of computation, AI, ARM, and RISC-V. And for that, I'm going to introduce you to the moderator of this discussion. It's James Wang, research analyst at ARK Invest. I hope you guys enjoy the show.
Alrighty, we have a great session. We may be the last of the day of the 3 days, but I promise you, it is not. It's not the least of importance. In fact, it is. I think, the most fundamental question that we have to answer if we want to plot the future of technology for the next 5 to 10 years. We invite many startups and CEO guests onto the show, and I think today we have two of the most unique people in the business. If you look at social media or consumer or enterprise software, there are hundreds of CEOs, hundreds of companies, if not thousands, working in those areas. But I really wanted to bring people in who are doing something different, who are doing something special, and whose model is unlike any of those out there. Today we have on the session, we have Andrew Feldman, CEO, co-founder of Cerebras. This is a company that I think unambiguously made the most unique and breakthrough semiconductor, both design and manufacturing innovation in the last year. They've made a microprocessor that is as large as a wafer. Just for context for what that means, we've basically made chips the size of stamps for the last 50 years. We now make one the size of an iPad. So it's an incredible achievement, and it will help us to chart the future of artificial intelligence. Andrew, welcome to the show.
Thank you for having me.
And also we have Naveed, who's the CEO of Sci5. Sci5 is a company that is commercializing a radically new model for microprocessor design based on an instruction set architecture called RISC-V. This is an open source instruction set. It is to hardware what Linux is to software, and I think it's going to have just profound changes to the industry for the next 3 to 5 years and onward. Welcome to the show, Naveed.
Thank you very much. Great to be on the show. And hi, Andy. How are you doing?
Well, how are you? It's good to see you again.
And Naveed and Andrew are, of course, chatting to each other because they're both old timers in the dying art of semiconductors. This is not their first.
We're back, James. We're back. We're not young, but we're back.
Wonderful, wonderful. Hopefully, with greater wisdom each time. Okay, so to help kind of just set the stage, I'm just going to go through a few slides for the non-specialists in the audience, so we know kind of where the lay of the land is. That'll take about hopefully around 10 minutes. And then we'll get into a discussion on where things are headed. This presentation is kind of something I put together, but I think it's kind of relevant and talks to both RISC-V and AI. So Andrew and Naveed, please feel free to jump in with commentary, with corrections. We can make this a live session. All right, here we go. So all technology, everything we're doing right now is higher and higher in the abstraction layer. But what really enables it fundamentally is computation. So I want to talk about kind of where computation is headed in the next 3, 5, 10 years. I basically have 3 kind of time horizons and themes to go through with different kind of areas of focus. If you look at what's happening today and what's going to happen in the next couple of years, that's on the start of the rapid adoption is the rise of artificial intelligence in computation, basically AI acceleration, whether it's GPUs or ASICs. This is a real business today, worth $5-7 billion, and it's growing very rapidly. So we need to understand what's happening there. The next phase, I would argue, is ARM in the data center. Today, the data center is ruled by Intel's x86 standard, mostly going to Intel, AMD taking some share. But ARM is a standard that has basically completely taken over mobile, and I believe will start actually making a dent in the data center. It's tried a couple of times and hasn't worked. I think it's really going to happen this time. And the final chapter is on RISC-V, which is an open source standard. It's the Linux of hardware. It's so new that people barely realized it was happening, and now it's just kind of on a stratospheric trajectory. It is going to have a profound impact. Maybe not next year, but it is already shipping, and I think we really need to understand what's happening. That's why we have Naveed on. So let's go through these quickly. So the rise of AI. Why is this happening? What's important? Well, everything you're using today, whether it's Facebook, whether it's Instagram, whether you're looking at YouTube video recommendations that just seem addictive, and how do they even know I want to watch this? How do we have all those technologies? We have those technologies and those intelligence, that kind of smarts, because we have basically brought to production an old idea called neural networks on a new level of scale, which is cloud and trained with internet scale data sets. Neural networks has been around since the 50s. It's grown roughly at the rate of Moore's law, doubling every 2 years or so. And then the kind of modern era came around in 2012 with a neural network called AlexNet. And ever since then, every internet company, every research university has been doing advanced research into deep learning and the complexity, that is to say, the amount of computation you need to train these networks has just grown dramatically. It's now growing in the complexity of 10 times every year, which is 5x the rate of Moore's law. So it's gone on a completely different trajectory. The only way this is possible is that we can build computers that are faster and faster to enable this kind of training. And so far, we've had the means to do that. And that is really with something called GPUs. These are processors originally designed for graphics that's become more generalized and capable over time. And their latest killer application is actually just using these processors to train artificial intelligence neural networks, and they've been extremely successful. NVIDIA has basically transformed its business from a gaming company to a data center company. So it spawned basically a new market in the data center, because Google and Amazon can no longer just rely on buying endless racks of servers to serve all our Alexa requests and Google requests. So they're buying a new class of silicon, these AI silicon. It roughly breaks down into 3 categories. There's a training market, which is the hardware needed to create or train these neural networks or algorithms so that they can answer your questions like, what is the weather, who won the game? There's the inference accelerator, which is after you've trained your network and you've deployed it, and you have, in a production environment, you have millions of requests coming in daily. How do you service those requests? This is actually the larger of the market right now. Intel makes a couple of $1 billion off this market, this is why Google built the first TPU. So this is a lower priced, lower powered, but more ubiquitous kind of use case. And then finally, we have the edge use case, which is basically in the device itself. It could be an IoT sensor, it could be the Amazon Echo, it could be a Tesla. Wherever you are, right at the point of the problem, the computer needs to give you an answer informed by artificial intelligence. It doesn't have time to consult the cloud. It will occasionally consult the cloud, but the immediate answer in milliseconds is delivered using this edge case. This has already happened. The latest iPhone chip already has inference, essentially an inference accelerator built into the A-series silicon. So this has already gone from a theoretical market to a real market. It's just that you can't really count the revenue as clearly yet. So it's probably a smallish market. This is what kind of, this table is basically what NVIDIA, Intel, and many of the companies are going after today. So last year I presented kind of the case for everybody is doing AI chips now. We have startups all of a sudden, funding for semiconductor companies had basically stalled out in the world of Silicon Valley. How ironic, but it had started all over again because companies were using AI for all kinds of use cases, and now venture capitalists were like, hey, we can invest in a new category of hardware. So that spawned this huge list of startups, which I've highlighted here in green. Blue are the incumbents who have the scale and the ability to build their own chips. The total funding here is in the order of billions of dollars, and this has been by far the most vibrant renaissance of semiconductor investment in recent history. Next, what has happened in the last year since kind of this AI Hunger Games started with this new burst of funding? We've had a couple of major changes. We've had some major developments. We've had our first IPO. Cambricon is China's domestic silicon maker for AI acceleration. They've filed for IPO on basically their version of the NASDAQ for $3 billion. So that is an incredible exit for a company that, well, it hasn't quite happened yet, but that's just, was created a couple of years ago. Intel has acquired Habana, which is an Israeli AI chip acceleration company, for $2 billion. This is their fourth acquisition, I believe, in the space. And this is also quite an incredible growth trajectory. Habana has raised maybe $100 million, was founded in 2016, and just in the span of 3.5 years to achieve a $2 billion exit is quite incredible. In terms of funding, of the private players left today in the kind of startups doing AI hardware, two raised relatively large rounds. GraphCore raised a round for about $150 million. They're based out of the UK. They presented in CogX in the past. And Samba Nova, which is a startup based in Silicon Valley, raised about $200+ million as well. So some of the existing startups are definitely maturing. They're seeing some deployments. GraphCore is in Microsoft's cloud. So we're moving past the point of just PowerPoint and into the point of shipping real hardware. And I think this didn't quite make it, but Cerebras, Andrew's on today, they're shipping hardware now to the Department of Energy, and they're using their chips to run those workloads. So that's to get a government contract this quickly out the gate is also just incredible development. Not all stories are positive stories. Wave Computing, which is one of the first companies to be in this space of AI and processor acceleration, they filed for bankruptcy. They raised $200 million, but that company is not going to be able to make it, and sadly, they won't be the last. So that's kind of the lay of the land for AI acceleration. Still very exciting, still growing, but not at the pace of frenzy that I would say from a year ago. The second kind of movement, I'll pass this one quickly since we don't have an ARM person on. We tried getting Ampere on, but they were not available. Is essentially, I think the world is going to move to ARM in the data center. ARM right now already monopolizes smartphones. There's no reason why they can't move up market like the trajectory of disruption and get into servers. That's a $90 billion business. Right now they lack developer market share. Apple is basically going to solve this problem for them because Apple is going to launch an ARM-based MacBook and transition their lineup to ARM in the next couple of years. Once that happens, developers will be used to developing on ARM locally. They will want to have a mirror environment in the cloud that is ARM. That's what's been missing. At least that's the argument that Linus Torvalds has argued for. So I think that will start happening. Next month, we'll probably start hearing about Apple's plans to bring ARM to the data center. This is very much real. Graviton 2, which is Amazon's ARM-based server CPU, is already beating their equivalent Intel processors in terms of price per watt and price per dollar. So Amazon is pushing it in addition to Apple. It's not just going to be kind of vendor silicon hoping to get share. And I think that the general trend this will enable is that the cloud has been the most powerful force in infrastructure in the last 10, 20 years. It's eaten the server manufacturers, so people don't buy from Dell and HP as much. Next, it will start eating into the silicon vendors, since it's very much natural for them to vertically integrate. So section 3 here, kind of the more 5-year trajectory. I thought it was going to be 5 years. Then I watched the recent interviews with Naveed, and the timeline is being brought forward each time, right? And RISC-V, which is the open source version of a computer instruction set, is really coming into reality. Here's the very simple way. You may not even have heard of RISC-V. Why should you care? Well, if you think about kind of the software ecosystem over the last couple of decades, it's gone through this very kind of natural development. In the beginning, operating systems and software in general was proprietary, and only the people who owned the software could work on it and monetize off it. Then Unix came around from AT&T and licensed it to a bunch of companies, and we had a more vibrant ecosystem. We had Sun, we had IBM. Many companies could benefit from it and grow from that, and that was better. But the final step was Linux, where you didn't even need to get a license. You didn't have to ask for permission. You didn't have to pay. Everyone contributed to the source code, and you can still build businesses off that. But that gave us the modern world where 80% of servers run on Linux, and we have free versions of these operating systems even on our phones. So that really kind of distributed the impact of that technology. Hardware is following a similar trajectory. We started off with proprietary. And then we went to ARM, which is license it from the company. That gave us, a very rich ecosystem. But even better is if it goes completely to open source, and that would be if people can just work off a common standard without having to ask for permission, and that would really accelerate its development. I'm just going to pause here. Naveed, do you think this is a reasonable analogy, and do you have any thoughts on this?
No, I think this is a reasonable analogy. This is actually not an analogy. This is the basis of why RISC-V got started. We do not have an open standard ISA. It is very unusual because in every other aspect, we do have open standards, and that we have seen the growth. So yeah, this was the very basis, and most people may not realize it started a long time ago. It started in 2010, and for the first 5 years, it was done at many universities. And in 2015, Sci-Fi was started, and so since that time, it has taken off in a big way. But I think it's a standard that has been adopted by all major corporations in the world. I think there are hundreds of companies who have adopted and are part of the foundation and are they contributing. So yeah, it is pretty much going exactly how your chart says.
Okay, glad that's helpful. All right, a few more and we'll just wrap up. I think what's really impressed me, when I first looked at RISC-V, it seemed like a nice little open source project from a university. Who knows if it'll work? That was like a year ago. And then I checked the RISC-V Foundation website last week, and the ecosystem and level of support they've built up has just been mind-blowing, to be honest. They have pretty much the A to Z in hardware and enterprise and cloud signed up as partners. They have all the EDA design tools you need to actually build chips off RISC-V, all the memory makers, and of course, all the universities as well, including my alma mater, University of New South Wales. So just in 5 years, I think the level of support, I have never seen any standard be embraced so vigorously by the community. So it's not just kind of standards, and it's easy to get your logo. Maybe you have to only sign up for a form and you get your logo on the web page. But real products are shipping. Western Digital is transitioning all their products to use RISC-V for microcontrol, and NVIDIA has a microcontroller based on RISC-V in every GPU it ships. So this is not kind of a theoretical thing. It is already happening. Okay, so that's kind of the high-level overview. I'm gonna just stop sharing I guess I could stop sharing here, and I will take one for Andrew first. Andrew, is there anything you want to add kind of to the narrative of where we are with AI? Did you feel like, and how has Cerebras done since the Department of Energy deal that you announced late last year?
Thanks, James. We've had an extraordinary 9-month run. We announced in late last year, we announced that we were delivering the largest chip ever built, and that we had solved a problem that had been open in the industry for 70 years, which is how you build a very big chip. And then we announced in November that we were delivering to customers, and we announced a win with the Department of Energy, and in particular, deployments in their supercomputer infrastructure. We build big, fast systems, the largest and fastest AI computers on Earth. And then yesterday, we announced a multi-million-dollar win with the Pittsburgh Supercomputing Center, in which we're building an 800,000 core AI supercomputer for them in combination with HP. So we've been able to, we invented technology, been able to deliver it, productize it, put it in customers' hands. And the problems that are being addressed with AI right now are just extraordinary. Our customers are using our equipment to study drug interactions for cancer treatment. They're using it for therapeutic invention for COVID. They're using it for physics simulations, for understanding self-driving and improving self-driving cars. They're using it for natural language processing. to power recommendation engines. The range of impact that artificial intelligence is having right now is extraordinary and accelerating, and it's a pleasure to be a part of an ecosystem where, when you deliver the fastest hardware ever built and you put it in researchers' hands, they help change the way we work, live, and play. And that's enormously rewarding thing to see.
Tell us about what it's like for a startup to get a win from a government agency this early in the game, because the HPC, high performance computing, is a multi-decade industry. The software stack is extremely complicated. I'm sure they want they don't want to just buy a machine that's good for one thing. They want to be able to utilize it for many things. How are you able to build software support for all the use cases they want, or are you focused on a couple of things to begin with? And Tabitha talks about how the compiler to I guess you're more in the training business, but for inference and I guess training, the compiler to make the hardware work efficiently for a given neural net is almost like a handcrafted problem every time there is a network. How would you characterize it, and how complex is that software problem?
I think we built the fastest AI computer by somewhere between 100 and 1,000x. And we then took it to the people who had the most experience in the world with blisteringly fast compute. And those are the largest supercompute sites. And we found a tremendously positive response. And they began acquiring Cerebrus equipment. I think we entered those in a collaborative mode. We certainly didn't think we knew everything about the supercompute market. What we knew was how to build extraordinarily fast AI equipment. And so we were able to, in collaboration with people like Rick Stevens at Argonne National Labs, Baranis at Lawrence Livermore National Labs, we were able to point these machines at some of the hardest workloads, some of the most challenging problems that the most demanding customers had, and that was great. I think your question about compilers is really important. I think making fast hardware is insufficient. One must also make it easy to use and quick to deploy. And we've spent more than 4 years building a graph compiler that allows you to write your AI models in industry standard open source languages, and still to get the benefit of our exceptional hardware. And that's no small challenge, and it's something that we've been able to do pretty darn well.
What is the preferred framework for people to work with your hardware?
We see most production environments right now in TensorFlow, and we see a lot of research being done in PyTorch.
And you support both?
We do.
Okay. Naveed, tell us about where Sci5 is right now as a startup, and maybe just the relationship between, I've talked a lot about RISC-V. RISC-V is an open standard, of course, but you're a company working to make that into a business. Why, I guess, tell us a little bit about your business model and why you think this is kind of the important way to go.
I think the first thing I'd like to mention is that we are very unlike a startup or a Silicon Valley company. I'll give you some numbers, which are so astounding that if somebody else who told me that number, actually I will not believe it. Let me tell you something. Last year, we released a video about RISC-V, 2 videos actually together, and we got 7.5 million views. In the history of semiconductors, I checked actually. I talked to my friends at Intel, friends at AMD, Xilinx, which has thousands and thousands of customers. Nobody have ever had anything like that. a typical press release, anybody who does in hardware, if they get 20,000, 30,000 views, that would be great accomplishment. On LinkedIn this year, we will get 10 million views. We are already over, I think, 4 million views as a company.
Naveed, it doesn't
So
sound like a semiconductor company. It sounds like you started a social media company.
Well, actually, if you think about that, I have 19,000 followers on LinkedIn alone. So I actually have quote unquote an influencer status in LinkedIn. So, I mean, I didn't know what an influencer is until I found I don't have any social, don't even have a Facebook page.
That's not for us, Naveed.
I know. But the point is that I think the following is much wider than the semiconductor industry. And that I think is the most exciting thing. It is bringing in more. I have argued for the last 20 years in front of GSA and everywhere, unless we bring in fresh blood, this industry is going to die. Because the average age of an executive in Silicon Valley is crossing 55 or 50 or something like that. We have to, and I think the biggest value to me, RISC-V is bringing fresh blood, new people, and they are not in US, they are not in China, they are not in India. They are all over the world. We can share statistics with you that over 170 countries have meetups and groups. What the hell are they doing about RISC-V? I have no idea. And last year we did 52 seminars around the world. And 52 seminars around the world, real seminars. And in some seminars, over 2,000 people showed up. I mean, 2,000 people in Lahore, Pakistan. Pakistan is not the semiconductor epicenter. So that is the volume what we are dealing with, the interest in RISC-V. And of course, vast majority are graduate student, hobbyists, people who want to do things in their garage. And this is, I believe, is the best thing that can happen to hardware. Forget ARM, forget x86, forget any chips, forget any startups. I think it will bring in new blood, new interest into hardware. I think that's number one. As a company, we have done very well. Actually, what we did was, as a company, that we realized that because of trade war and any other things, we sort of split ourselves. So we are really three companies. We have a company in China, separate from us. There is a company in Korea, separate from us. And so there are three companies, and sort of we are growing together. We are an independent company. But together today, we have close to 900 employees. And we have raised close to around $350 million in the last year and a half, 2 years. So I think it has been very well funded. Our people who funded us include Intel, Qualcomm, Samsung, Hynix, Western Digital. I can go on. All the major semiconductor companies have funded us. And this is not just true here, it is true worldwide. I mean, in China, we have got good funding from Chinese investors. In Korea, we have good funding from Korean investors. So I think it is a much wider phenomena than just a startup. So I think our role has been very simple. We are working with universities. There are over 500 universities who are teaching RISC-V. We think that is the future of RISC-V. We are working with governmental agencies around the world, many of them, around 15 or 16. We are working with RISC-V Foundation. We are on many technical committees to promote open standards. We actually contribute codes to open standard, and we have many codes available for free. People can download from our website.
I think the university point is huge. I mean, CUDA became big, NVIDIA's programming standard, partly because they did so well evangelizing universities.
Yeah, so in our case, since all the major textbooks in architecture have been now switched over to RISC-V, and there are books available in Chinese, Russian, and many other languages in RISC-V. So I think that is doing very well. I think that is the entry point, and that's why you have millions of views, are all these graduate students watching stuff on our YouTube channel. But I think commercially, I think we have done very well. This year, we should see over 200 million in our booking. We know commercially we started only 3 years ago. So 3 years ago, we had like 1 million, 2 million booking. Today, we are over 200 million. So commercially, we have done, and this is just the US company. I think if you include our other companies, we are doing very well. So I think commercial adoption, we have 175 design wins. in the last 2 years. We have 89 customers, and our customers are not startups. Our customers are all major companies in the world that I mentioned earlier. They're all our customers as well.
Okay.
So I think commercially doing very well. I think university side is doing very well. I think we have good collaboration with the governmental agencies around the world and Describe. So all in all, I think I'm extremely happy with the progress we have made in last 3 years, not just for sci-fi, I think for hardware industry as well, because I think it will breathe new energy into hardware, which I have been arguing for a long time. We need it, and it will bring a lot of new blood.
That's great perspective. And I love how you're more pumped about the wider ecosystem than just your own company. Tell us a little bit about how, I guess, as simply as possible, how your business model works. I listened to your presentations on YouTube, and you basically have a cloud interface. You're like AWS. You instead of designing a chip by hiring a bunch of people, you log into a website and select some templates and make some modifications, drop in your IP, and you can order chips. What is the cost? What is your monetization model? Do you take care of the back end? Does TSMC's chips come to my door, or do I have to download the file and go talk to them? How does all that stuff work?
So we have two business models for two types of customers. We have customers who are people who know a semiconductor business very well. They have their own design teams. So for them, all we do is just give them the IP. It's very similar to ARM, except the delivery system is very different. So the delivery system is not that you call our salespeople. You go to our website, and there are a bunch of templates are available for different quality of cores and type and size and performance, and very low-end embedded cores, which we call the Series 2, Series 3 cores, all the way to Series 8, Series 9, which is high-end cores. So you go to the website, you modify it, you play with it, you check the performance, you see what would you like, and once you are done configuring it the way you want it, it's quite extensive what you can do with it. And thousands of people go to our website and do that. And once they are done, then they click a button called build. And then we will actually build the IP for you, put it together with the collaterals, and we'll ship it to you. So that is our IP. And this is for semiconductor companies and people who, they are actually building chips themselves. But a large part of our business is system companies. And those system companies actually want the chip done. And so for those people, we are building an interface, just like for our code, we have an interface on the web. We are building for the chips as well an interface on the web. I'll give you an example. It's a public example, so it's well known. About a year ago, for this chip template on the web, we did an example with Microsoft Cadence and TSMC. And we basically said that we can modify a template based on customer need in about 1 month, and then tape out a chip that will take another 2 months. And then you actually get prototypes in your hand about 3 months from a given prototype. And so people said that looks ridiculous. But anyway, they said that if you can do that even in 3 months, we will consider that is a great. So what we did was we started it, and we were not able to do that in 1 month, but we were able to do that in 5 weeks. So in 5 weeks, we took a template, modified it to the customer's needs, reconfigure it, taped it out on TSMC. Chip came back after 2 months, ran at 1.5 gigahertz, 564-bit cores, PCIe, lots of other IPs on it. So the customer has a chip in about 3.5 months from the time they went on our website and start modifying a template. So that is the approach we want to take. This is a very narrow approach. You have to understand that. It is for a segment where we have already designed a template. Customers identify that, okay, they want this particular template. Their chip is very similar. And then the limited choices that they have, they can use those to configure the chip. Then we tape it out for them, and they get a chip in their hand. So it does show up on your doorstep or on your lab, wherever it shows up. And we take care of back-end, package, test, everything. It's a complete chip logistics solution for those customers, the system customers.
That's incredible. And which of these, I guess the first one is a higher margin business, I guess?
Yes. The first one is the IP business. So it's a 95% margin business. Second is a ASIC chip business, 35-45% margin business.
I see. And where are you getting most of your, I guess, revenue today in terms of these two models?
Our revenue is going to be, our goal is to be in 25-75. IP should be 25, and chips should be 75, because of the very nature of the size, the volume of the chips, and so on and so forth. And we see people like Andrew. Now, Andrew has an extremely incredible team, but we see many people like Andrew wishing to do their own chips, but not having the expertise, not having all the width of the team that Andrew has. So those are the companies we feel that we can be a good solution for them. Right now, they have very few solutions, and if you look at many companies, system companies are beginning to build their own chips. So we could be a help to those guys, and that is where we see majority of our business coming from.
Awesome. Andrew,
I think one way to think about what Sci5 is doing is, we spent in the industry years on this trajectory where building chips became more expensive and more exotic. It had millions or tens of millions of dollars of NRE. It required extremely exotic skills in your team. And that meant fewer chips were done. And I think what Sci5 and Naveen and his team have done is to drive down the cost of building custom silicon for many projects. Drive down the cost of exploration, drive down the cost of ideation in hardware. And that was something the industry needed. And I think what he's talking about in sort of a renaissance of interest in hardware is because we can, through Sci5, we can now do it at a very low cost. And that's a very powerful thing for the entire ecosystem. And that's extraordinary.
Andrew, since we're talking processors, last time we chatted on our podcast, you said Cerebrus delivers a whole computer. It's not just an add-on, and you don't use an x86 processor. Have you talked about what CPU you use?
We don't use a CPU in our machine at all. We design the instruction set. We design it and optimize it for AI work. I mean, we are a specialist, dedicated hardware. We're not also trying to do graphics. We're not also trying to do gaming. We're not trying to do 100 things. We are a cheetah. We are built to attack one problem, and that problem is artificial intelligence.
Well, how do you connect to the host? Like, how does the whole thing fit together?
Think of us as we build a 15 rack unit computer, and the I/O is 12 by 100 gigabit Ethernet.
Through your Ethernet attached device.
We connect to switches or upstream servers where the data in the training set or the inference data is kept. The data is streamed to us, and we process it and produce back the learned results, the trained parameters, or if it's inference, we send back the classified results. Now, somebody's asked a question I saw about what's next. I think you're in the chip business, you're always trying to go bigger, faster, better. And I think as we look forward, we're looking at more aggressive geometries. Today, we're built at the 16 nanometer at TSMC, who was an extraordinary partner to us. We're built at the 16 nanometer. I think we're going to go smaller. We're looking at a whole set of additional inventions to drive up on-chip capacities. We are trying to take the same innovative approach that led us to build the largest chip ever by 56x to the next level, to continue to do fearless engineering. And it's an enormously exciting project.
If I may add, what Andrew and his team is doing for people who are not from this very specific industry, we use a term called domain-specific architecture. So they are not beholden to an architecture like x86 or RISC-V or ARM or anything. They're simply saying, here is a problem. What do I really need to solve that problem? And so they put together an instruction set to just solve that problem. So if this team is given another problem, they will again look at the set of instructions they need to solve that problem. So it would be very difficult to match the performance of such system. But I think just for other people to understand that They just didn't do that. If they would have done that, I think they would have been celebrated in Silicon Valley and world over for that accomplishment. They then combined that with wafer scale integration and put a wafer scale chip. I think that combined two things together, they're getting this incredible performance. And they've gone 10 years ahead of everybody else. So I think so the keyword I would like to is domain specific, and I think this is what's going to happen in future. General purpose computing is not going to be the way of the future. I think Andrew and his team is trailblazing. You'll see other companies following their footsteps in other areas, not AI. Of course, there will be copycats, and that very natural happens. But people will pick up other data sets and other application areas. Like, for example, somebody might say inside AI for drug discovery, it's a specific problem which is even more specialized than what Andrew is looking at, and make even more specialized. So I think research and it might go in that direction, which I think Andrew would probably say it's a good thing that what they started is the first step. People will go deeper and deeper, and we can build big chips. And we know that's what is needed.
I love the bromance that's going on here. Everybody knows exactly what they're doing.
We've been we've been in this industry together a very long time.
And actually, we have somebody in common between us. Both of our companies were funded by Pierre Lamond, a legendary figure. and if you have a father like Pierre Lamond, which Andrew and we both learned from the fire.
Wow.
And I think we are very thankful to people like Pierre. The reason I'm sitting here and Andrew sitting here is for a large part that the training we got from people like Pierre. And so I think we have a lot in common going back 20, 25 years.
That's awesome. Andrew, I just wanted to ask you, I think the most important thing that's happened in your space, high-end AI acceleration, of course, is NVIDIA's announcement of the Ampere chip, the A100. I think it's kind of pretty much what we expected.
Yep.
Were there any, did you have any unique perspective on that, kind of where they're headed? They started, and NVIDIA obviously started very domain specific, basically the rasterization algorithm. And now they've moved, because they're an established player, they want to appeal to as many parallel acceleration workloads as possible. So they support the whole HPC stack, AI training, AI inference. But they're basically trying to build the largest chip possible using basically a conventional style. What is it like competing with them? You talked about the WSE, your chip, being able to do new kinds of workloads since the architecture and the memory layout is so different. Have you seen researchers tap into your processor in a unique way?
So there's a lot of questions there. I think first, NVIDIA is an extraordinary company, and they pioneered the graphics processing unit and made it a distinct thing, not part of the CPU, but rather a distinct thing. But the part is called a graphics processing unit for a reason. It's because every aspect of its architecture is tuned for graphics processing. And when you take an architecture and you try and remodel, right, you struggle a little bit. The foundation was built for a different house. And their new Ampere part is a solid part. It's 2 and a bit times faster than their previous one, about what you'd expect when you do a shrink in geometry from 12 to 7. I think that they have invested a great deal in it, and they have many customers. And I think that they were important in the evolution of AI.
Okay.
But I think right now we're winning the largest accounts with the hardest AI problems.
All right, we do have to wrap up. Unfortunately, we're right up against the time limit here. Andrew, Naveed, thank you so much for joining us. Folks who are interested, please check out their websites. They're doing amazing work. And thank you for all the people who tuned into CogX this year.
It's a pleasure. Thank you for having us. Good to see you guys.
Thank you so much. Bye-bye.
Thank you very much, guys, for such a brilliant final session. And we're now going to wrap up on the last session on the cutting edge stage. Thank you very much for joining us at CogX this year.
which again is more time. And obviously a one-on-one meeting can take a whole hour, which is an entire session. So,
Amazing.
Thank God we had a very big number of people attending, because actually that audience was spread between all these different ways of interacting. And we didn't really know who was going to go where, but I've got the latest stat here. We actually had 13,721 one-on-one meetings set up on the platform, which is just, I mean, that's an amazing number. At the physical event last year, it was 3,300. So this year, 13,721 meetings.
That's amazing. And I heard that Eleanor, our head of content, got matched to her husband. So clearly the algorithm was working really well.
Extremely well. And then, but in addition to that, when you have a meeting, you can go video, you can go audio, but you also have a chat window. And we had 17,074 individual messages going back and forth on the chat window, which I also thought was pretty amazing.
Wow, gosh. It's I hope that those of you watching were some of those numbers of people that had connected. The plan, just to let everyone know what our experiment, is that we would like to, as you all know, the theme of this year's conference is how to get the next 10 years right. And we would like to cheers to that. And so what we would like to do at about, we'll still find out, but in the next few minutes, what we're going to do is we're going to welcome in our whole team. As in the broadest set of people that have been working on CogX, our team, the amazing crews that have joined us just for the last 3 days. And we will say thank you to you, our audience, and we'll say thank you to them. It's something we do every year. It's a tradition that we uphold, even in the virtual environment. And
Can I just ask you a question, Tabitha? Did you ask anybody if you could get the whole team on at once?
I did. I asked a few times.
How are we even going to do that?
Me. Well,
I think there might be a reason why getting 200 plus people onto a stream is going to be pretty hard.
Yeah, so we're very lucky. The crews that we work with are quite phenomenal. And when I asked them on day one, they said absolutely not. When I asked them on day 1.5, they said no. Day 2, nah. But today, I think everyone was feeling really confident, excited, and up for a challenge. Apparently, there's something called a Scott Mackay, and everybody said that it was an okay thing to do. So hopefully, this is going to work.
Okay, so this is, but let's be clear, this is an untested experiment that nobody's seen before, that you just threw on the crew in the last day.
Yeah, I would say maybe hours, last few hours. But you know what?
I thought I was the risk taker in the organization, but like.
Yeah, I just, I had a vision. No, I'm teasing. I just feel like it's so important to say thank you to all of these amazing people. And what I want to do is a big cheers. So I've got some water ready. Charlie, have you got some wine ready? I've also got some chocolate. So if you'd like to cheers with chocolate, wine, water, whatever you'd like to cheers with, we're going to do a virtual, almost like a Mexican wave cheers. So how this works, and you can see on my Twitter page, you need to take a picture of yourself like this. Oh, got all the hands the wrong way around. Like this. And post that on Twitter with the hashtag, it would be good if I remembered the hashtag, with the hashtag BigCheerCogX. And we will find the cheers that we love the most, and we will send as many CogX hats out as we can. So get cheersing when we start cheersing. So once you can see this experiment live and everyone's on the stream, you can start taking your pictures and start sharing them on Twitter. Let's hope this works. Now, I'm being told that we're not yet ready. It's a little bit longer to go. So what I was thinking instead is, Charlie, do you want to show us what shoes you've been wearing all CogX? Because I thought I could show the fact that I've been wearing Crocs. Ooh. All CogX, every single way of the way through. And normally I have to wear heels, and normally halfway through I sneakily get sneakers on like Charlie. But no, this time I've gone full blown Croc, which my partner will tease me relentlessly for, but will find that quite amusing. I hope all our speakers have also been wearing ridiculous shoes, because in the virtual world, you don't even need to wear anything you don't want to. What's your favorite part been, Charlie, of the festival?
I was going to say not having to wear shoes.
Yeah.
I would normally be wearing these the whole time, and my team do mock me for wearing red trainers, although I did walk past a few shop windows with them in recently. But
well, the good news. The good news is that everyone's there.
No, they're not.
I think it's worked.
It's not possible.
Okay.
There's no way. There's no way they could have done this.
Bring them in. Look at that. Oh my gosh. Okay, so we're going to start by thanking. Look at this. Keep going. This is so brilliant. So we're going to thank our headline partner, Microsoft, our lead partners, IBM, Quantum Black, McKinsey, UiPath, Illusions, our sponsors, Baker McKenzie, VMware, our stage partners who brought you all of this, the Fabric Ventures, Janet Hull at Createch, Alan Turing Institute, Springer Nature, Institute for the Future of Work, Tech UK, Digital Catapult, Tech Nation, Teens and AI, Camden Learning, ODI, Office for AI, the CDEI. Charlie, who brought us the events partners? I'm exhausted.
Our amazing side event partners, Tom Cheesewright, Best Practice AI, the UCL AI Center, the RSA, the Royal Society of Literature, Rainmaking, the Future Society, Aspen Institute UK, Mary Claire, the ODI, and of course, back to our lead partners, IBM, Quantum Black, and our headline partner, Microsoft. And last but not least, our wonderful new CreateX stage with the UK's creative industries body. So what an incredible group of partners we had, not to mention the 300 plus exhibitors that were in the virtual expo.
It's just quite amazing. I'm watching as everyone comes off. This is a team of over 160, because I was told that was the max, and then we did sneak a few more in. So this is a huge set of people. I mean, I'm just watching.
This is amazing.
So much love.
Oh my God! Look at them getting really fancy on this.
Doing some fancy.
Hey, Janet.
Janet, what an amazing group of people. But really, we want to say a cheers to all of you, the audience. So I think we're almost ready for the big cheers. What do we feel like? I want to check on Twitter and see whether people are ready. For our Mexican wave, what do we think? I think we've got 30 seconds of everyone holding up their wine, water, chocolate, whiskey, beer,
The
orange
cheers is going
juice.
on so long, people's hands are getting tired.
That's the waving. We need the cheers now. My Mexican wave, yeah, it's happening. And the Mexican wave's off. The cheers to getting the next 10 years right. Let's cheers to getting the next 10 years right. Let's cheers also to getting this stream next year so slick. And there it is.
The cheers, the cheers.
Cheers to getting the next 10 years right. Cheers, all of you. Thank you so much.
Thank you so much. What an incredible, incredible 3 days. 44,000 viewers in the end across all of those stages. Just thank you so much.
We'll see you all next year.
We'll see you next year.
Bye.
Bye for now. Bye. And it's a wrap.
It's a wrap. Woo!
And thank to you.
Cheers.
And thank to you, Tabs. What an amazing, amazing journey it's been to now. And go give little Otis a hug. I'm sure he's been missing you.
He has been. Thank you. See you all soon.
Bye from us. See you soon. Bye-bye.